Artificial intelligence. Everybody now talks about artificial intelligence. ChatGPT has changed our lives as teachers. Yeah? I mean, right now, the new law of higher education, there will be no bachelor thesis written because ChatGPT is writing the bachelor thesis better than the students. We, the teachers, are learning from students how to use ChatGPT for benefit. So far, we consider it our enemy, our adversary. Yeah? But we are learning. Okay, wait, we get there as well. But today, we will be having a conference and workshops in the afternoon about how actually AI can help our health, human body and human soul, our physical and mental health. I am myself very curious what we will hear today, and I would like to ask the rector of the university, Professor Králíčková, to say a few words first.
Thank you. Thank you, Honza. Dear colleagues, dear friends, dear guests, it's my great pleasure and it's really honor to meet you here by first AI for Body and Soul meeting. And it's definitely a great honor to have here today keynote speaker Peter Kuhn, Professor Peter Kuhn from University of Southern California, who I know will be super interesting. So I'll be very short. I just want to say three things. Artificial intelligence definitely has extreme potential to help us all solve the problems of today's world. There are plenty of challenges that are here to be solved by us, by the knowledge that we have, and maybe with use of instrument of artificial intelligence. And I'm sure that today's speaker will bring us all the insights into this. Emeritus Dean of Faculty of Mathematics and Physics, Professor Jan Kratochvíl, was one of those people who a few years ago started prg.ai. We have here today some people from prg.ai, an attempt of City of Prague, Charles University, Faculty of Mathematics and Physics, Czech Technical University, and few more players, Academy of Sciences, to really bring artificial intelligence in heart of Europe and to make Prague one of the centers of artificial intelligence that will help us all solve the problems of body and soul. So I'm really happy that today's meeting is one of the meetings where we will make further steps in that. I would like to wish you to have a fruitful morning, and I'm definitely looking forward to meet you again, all, by some further activities. I hope you will enjoy it, and let's enjoy the speakers and today's. Thank you.
Thank you, Milena, and it's my duty and privilege to introduce the first speaker, Peter Kuhn. Part of the introduction was already done by Milena, so I can skip some information. I would like to say that he actually grew up and started his university education in Würzburg, Germany, but he got his master degrees from Albany and PhD as well in physics. And then he joined the Faculty of Medicine at Stanford, was a founding member of a research center, Michelson Center for Biosciences. What biosciences? Convergent Biosciences. I cannot read my handwriting. Sorry for that. But also founder of a company, Epic Sciences, in 2009. And he wrote over 200 papers, has 27,000 citations to his work. And with no more ado, please, Peter, tell us your views about how AI can help us as human beings.
Thank you. All right, thank you. It's great to be here. Actually, it's my second time here in 2 weeks. Oops. Yes. Well, maybe in the future, actually, I don't need a microphone anymore because ChatGPT will just pick it up and run it in multiple languages all at the same time. It's actually my second time here in 2 weeks because I actually serve on Milan's International Advisory Board for Charles University, and actually we have been working together for about a decade now. And what Jan actually forgot, because I don't think I told him that, I thought he knows, but I'm actually also an honorary professor at Charles University. And our interaction goes back to a time period when I first joined the University of Southern California, and one of my first conversations with another faculty member, Yolanda Gill, who is an AI scientist. And back then it was not that frequent to come across people like her. And I always enjoy asking people, you know, what's your goal in life? Why do you do what you do? And back then, it was striking. She's like, look, Peter, my goal with my science in AI, not using AI, but science to advance AI, that goal is simply to get to a place where an AI can actually get a Nobel Prize. And I thought that was a striking comment, right? When we think about a Nobel Prize, it's meant to be a de novo discovery, right? It is not an incremental, it is in the end, every discovery is an incremental process of a human being, right? But this fundamental aspect of, can we get to a place where actually a machine approach will get to a brand new discovery? And so that has always stuck with me over the years, and so we'll see where we get. Now this is interesting. This is a great talk, but I must have copied the wrong PowerPoint. Now this is super interesting. So this is actually a keynote, and I apologize. We will have to switch talks, I think. This was a great keynote. Jorge Nieva is actually a dear colleague of mine, and we played a game. This was at the American Association for Cancer Research a couple of years ago. We had about 24,000 people in a live audience. And we did this controversy of physicist versus physician, which was great, but not what I wanted to do today. So I'm going to set this down for a moment.
So in the meantime, I will continue with the introduction of Peter. There are some other lines that I had prepared, and I didn't want to waste time, precious time with. Peter has devoted actually his professional career to cancer, but he and his team have breakthrough discoveries in the new ways how cancer is carried into and inside the human body. And he devoted all of his life to application of these to personalized medicine and individual patient care. And I think this is really a field where AI can be most useful. So we're getting to 54% already. The previous talk got copied in a few seconds, so probably this will be a much heavier talk. Yeah?
Můžeme ještě případně spustit tam absolutně.
I teach one class in the spring semester, and I decided this year not to be afraid, but I said this class, the final paper of this class has to be written entirely by prompt with answer on any given large language model you would like to use. So this is a class where we talk about applications of molecular biology in medicine. So this was really about early detection of cancer and what is the next round of experiments that need to be designed. And we always do we do 4 teams, so we split the students into individual teams, and then the final paper that has to be written, is typically your 12-page, your standard 12-page paper. And I said I don't want any of this to be written by you as a student. I want everybody to figure out how to prompt a large language model paragraph by paragraph. And that was a fascinating exercise. I kicked it off with the same as what I'm going to do today, and that is when I saw the title, Body and Soul. There's lots of things about what we do with soul at the Institute, but none of it is driven by AI. So I decided to do exactly what I did with the students. I told the students that next week I will have a dinner with a faculty colleague in Los Angeles. And I said, can you find me a restaurant that's somewhere close by where 2 faculty colleagues can meet, have great food, and have an intellectual conversation, right? For each one of you, you probably all are going through, you're iterating right now, like, this seems pretty obvious. Yeah, okay, fair enough. Maybe a modern place, interesting, stimulating, not too loud, right? Because you want to have a conversation, etc., etc. So when you do that, you get a set of restaurants, and I don't know whether you recognize them or you don't. I used Prague here as an example. In fact, actually, what the students did was that they actually looked for healthy food when I told them great food. And what happens with ChatGPT in Prague is exactly what happened with ChatGPT in Los Angeles. You exclusively get vegetarian, vegan food options. So the sensitivity of these large language models to the prompt is, of course, incredibly important. Now, if you look at these restaurants, I don't know whether you would consider them for a night out with a faculty colleague. I have been to lots of outstanding restaurants in Prague. These were not on that list. Now, Jan, of course, knows why I asked him that same question. Okay? So, his answer, of course, did something really interesting, because he knew exactly what I was looking for. Great food was important, but what is great food, right? That's a bit vague. But he knows exactly what, at the end of a long day, 2 faculty colleagues would actually want to experience, right? Because that's what that is, having that conversation. So it is really very, very interesting to think our way through of how these large language models, where they work, where they don't work, and how fast you actually fall flat on your face today with the current models. That was super fascinating. The students actually, at the end of the semester that we just had, there were so many anecdotes like this, where the model would just go into a place and it just can't recover. It spirals down into just spewing out nonsense, and it just can't recover from there. And the students all ended up writing a paper, all writing it themselves with standard references, because they just couldn't get beyond the introduction. The introduction always sounded great, but going deeper was impossible. Now, we will see how the next iterations, for those of you working in that space, and I had a lot of follow-on conversations with people who are developing these models, how the next iterations will get better at that. But this was just a fascinating observation. So now another conversation with another faculty colleague, Dean Meltzer. She is the dean of our medical school, and she's also a radiologist. And as a radiologist, there's something super interesting when you talk with them, because when they look at an X-ray, or when a pathologist looks at a slide of a tissue, they can very quickly see that there is something wrong. Each one of you actually who does something that has to do with images. So I grew up with X-ray diffraction patterns. And so I spent 10 years at synchrotrons around the world, and I could walk by any given experiment, right? And I can, within a split second, I can say whether this is a good experiment or a bad experiment. So the radiologist can very quickly look at an X-ray and say there is something wrong. Most of the time, in fact, they can point to it and can say, here is a tumor, or here is this wrong, or here is that wrong. But sometimes they can't. And they have to say, there's something not right, but I don't know what it is. And that's complicated, because how do you make that actionable? Now, for her, this revolution that we have seen of AI being applied in radiology over this past 4 or 5 years has been outstanding, right? Because all of a sudden, she can use those tools to actually put some statistics behind her, something is not quite right. Because the AI models are actually able to say, here is that particular risk that that patient has. So as Jan was saying, and we use ChatGPT just like we use the word, in the US at least, we use the word Xerox for copy machine. It's just a representation of these large language models. But it's really, really important, because last year was truly one of those freeze frame moments. And I tell this all of our students, I can't emphasize this enough for everybody to truly remember that particular part of 2023. Lots of things in 2023 we don't have to remember, but this is one we should. Because that part of how in 2023 these models burst onto the surface, into the public square, is something that doesn't happen very often in our lifetimes. And everything changed, not just because the technology changed, but what has changed is how it became a conversation in the public. And that is super important, because that is how we actually make progress, because all of a sudden there's a huge, everybody is invested into it. Not just from a money perspective, but from some sort of emotion. I don't think there's anybody on this planet at this point where AI does not trigger a particular emotion. Okay, and so that's what makes this 2023 really a freeze frame moment. And it's interesting, right? Because for those of you who work in mathematics or in computer science or in AI, right, you will all say, yeah, but Peter, we have been doing this for a really long time. Right? Well, why is it so, why do you say 2023 is so important? And it's important because it burst onto this public square. And that is just something incredibly unique to actually happen. So there's a couple of examples, again, has been around for a long time. Tempus Labs is one of those companies, Eric Lewskowski, who started Tempus over about a decade ago now. His wife had cancer. He at that point had Groupon had just gone public. He made an enormous amount of money by figuring out really how to use the internet as a marketplace and build Groupon. It was actually interesting because Tempus AI in 2021 was rebranded as Tempus AI instead of Tempus Labs. When he founded it, his goal was, right, to build a laboratory that can evaluate patient samples to look for cancer and look for targeted therapies in cancer. And so back in 2015, AI was not a common word, and it didn't matter in the public. So he really focused it on the actual purpose of the company, and the purpose of the company is really to find cancer. Okay, this rebranding I thought was just a very, very curious bit, but he was one of the first people who really took this very large-scale approach, and he took it into a company to ask this question of, can we take histology together with genomic sequencing, together with protein data, together with clinical data. Of course, today we call this multimodal fusion, right? Or model fusion. So it's a very interesting construct that has been in the works for a very, very long time. But all of a sudden today, over this last couple of years, with the developments that have taken place, we're actually in a very different position of how do we actually do this. So I want to give a couple of examples here really quick for this first part, or for this, whatever, for this part of the talk. I want to give a couple of examples really quick to give you a feel for just how far we have actually gone. And I'm going to look at X-rays, at MRI, ultrasound, and microscopy. So when we think about radiology, there was a trial that was called the National Lung Cancer Screening Trial. So this was a trial that was actually funded by GE with about 25,000 patients. So these were all people who had a smoking history and were at risk of lung cancer. And the question that was asked within the NLSC trial was whether a chest X-ray was as good as, or worse than, or better than a low-dose CT scan. And that trial was actually super interesting because when that was published in 2011, the rate of false positives was actually, in many ways, one could argue, out the roof. Right, because the true incidence of lung cancer is fairly low in this population still, despite the smoking history. So having a 27% false positive rate is, of course, makes no sense at all, right? Because you're giving all these people an answer that says you might have lung cancer. We just have to look further. We don't know yet. And but it definitely showed that the low-dose CT scan was better than a chest X-ray. It was followed by a European trial, which was called the Nelson trial. And what the Nelson trial did was, again, a couple of years later, not necessarily just because the Europeans might be smart in terms of their trial design, but what had really happened was that the interpretation of the X-rays had really improved tremendously. So all of a sudden, we dropped by about a factor of 10 in terms of the false positive rate. Now, this is still too high, of course, right? But it's a massive progress that has taken place. So it's been super, super interesting. Now, over the past, and I think that Sybil paper came out in 2023, was a deep learning model that is now using that data to actually not just ask the question, very, very interesting, because they could have asked the question of, can we improve on the false positive rate? That's actually not what they did. They asked the question that said, can we predict who amongst those patients who do not currently have cancer will have cancer in the future? Right? So it becomes very, very interesting that when we have enough data to train these models, and when we have enough clinical follow-up data, and we'll come back to this over and over and over because that's a critical piece to that, is the quality of the data that we use. And so that, to me at least, was just one of those really outstanding examples of not just being able to diagnose today, but to prognose health for an individual patient. This is an interesting other example using now microscopy. Again, all of these deep learning models, of course, work incredibly well when it comes to images, right? So that's why, again, whether it's X-rays or MRIs or ultrasounds, or in this case, microscopy images. What this example here on the left-hand side is, so when, let's say, a woman has a positive mammogram, goes through a diagnostic workup, and so you find a nodule in the breast, you go in with a needle, you take a sample out, and then you slice that sample up, and it goes down on a glass slide. It is stained. What you see there, that bluish stain is an H&E stain, which is essentially just a contrast enhancer for all intents and purposes right now. And the pathologist, any pathologists in the room? I have to be more careful if they are, but a pathologist looks at this, and in many ways looks at whether or not it looks regular or irregular, right? Because a healthy tissue has a very regular look to it, the way cells are block by block next to each other. And when there's an irregular look to it, then that is an indication of cancer. Now, I still, even though I have been working with pathologists for 2 decades now, I still cannot read an H&E stain. This is not trivial. I still would not be able to actually tell you on the left-hand side which part of that is cancer, okay? So this still takes some real expertise to actually do this. But what's fascinating is that, of course, cancer at its very origin is a disease that has a genomic background, a genomic disorder, right? So it's actually the genetics of the cancer cell is really what's broken relative to the healthy cell. And that reflects, of course, in the growth pattern. Now that's not, in the beginning, it makes total sense once you start thinking about it. But so what these guys have started doing, and there's now a number of examples like this out there, what these guys started asking was, can I see a particular mutation? So one gene modification, can I see that in the growth pattern of the H&E stains? Because what would normally happen is that the pathologist would say, okay, this is cancer. I need to figure out what subtype of cancer is, et cetera, et cetera. How do I do that? So the sample would get scraped off and be sent off for sequencing. The question we're asking here is, do we have to do that next step at all? Or can I actually derive that just from the growth pattern itself? Can I get a genomic pseudo-analysis from out the growth pattern? So that, I thought, is one of those other super, super interesting constructs. The next one, which is now emerging, is this construct of opportunistic AI in medicine. Okay? And there was a series of papers. Eric Topol actually put this list together just a couple of weeks ago. And I thought, especially if we just look at the top two, for that matter, that top paper just came out in 2024. And again, it's using standard chest x-rays. Most of the time, actually, these are the x-rays that come from the lung cancer screening trial, so taken for a totally different purpose. And they're asking the question of, can I see something else in those x-rays? And in fact, it has a so MAZE is that major adverse cardiac event predictor. So using a standard chest x-ray is a better predictor than anything we have in the clinic today of a 10-year risk of a major cardiac event. So that's super interesting, right? It's an x-ray. It's not some functional readout. Unbelievable. The second one, just as off the wall because you wouldn't expect it, is actually being able to diagnose type 2 diabetes from a chest x-ray. Right, so one can start asking questions, and again, all of it has to do is, and I just talked to somebody who is structural bioinformatics, right? So in the end, all of this is just structural biology at various scales, right? Whether we look at the gene level, at the protein level, at the cell level, at the human level, one way or the other, healthy versus non-healthy, reflects itself in structural changes. And that is what we can start detecting here. So the real question that starts arising is, what is the kind of problem that I actually want to solve? What is it that's worth solving? Because this would argue that given the right data, and we have to be thoughtful about what right data means, there's all kinds of just absolutely fantastic opportunities in medicine today. So this is that type 2 diabetes one. This is that example of predicting heart attacks 10 years in advance. On the right-hand side is what's currently used in the clinic, and on the left-hand side you just see how the different risk prediction curves are actually much better separated by just using a chest X-ray. So absolutely fascinating. These papers are actually really fun to read. So next, I want to go more towards the premise, so something that we don't have the evidence yet, but the evidence that we're currently building. And so this is when this talk now switches over very much into the cancer world. Just going to do a quick time check here. Okay. And these first papers that I talked about now, when you look at how the authorship is put together, which is always interesting to look at. It is definitely a collaboration between computer science and medicine, because otherwise it would be impossible in terms of just getting that medical context and really figuring out what data is available, etc. But I believe as we go forward, that collaboration has to actually be much, much deeper. And this is when we start talking about augmented intelligence, and so this is the machine-human interface, iterating over and over, but it actually also means between different human beings, right, where we have to augment each other. We might actually not be able to learn. I will never be a pathologist. But in every question that the pathologist asks and I'm trying to answer, it is not a straightforward, here's a set of instructions, Peter, go and solve the problem. It is this iteration that we really have to do. And that is what is probably one of the most complex issues that we will have as we go forward, of how do we actually work across the disciplines and work with each other to solve particular problems. For us, and when Jan mentioned the institute that we founded at USC, is the Convergent Science Institute in Cancer. And Convergent Science is really meant very, very purpose-built for specific questions where we have a point of convergence. In our case, the point of convergence is really the improved outcomes of a particular cancer patient. So we're not just broadly talking about, hey, we do cancer research with advanced methods, because that gets complicated when we try to work across disciplines. But in our setting, actually, we ask very, very specific questions of how do we actually improve the outcomes for specific cancer patients. For those of you who don't live in the cancer world, the primary tumor, and whether this is a breast cancer or a lung cancer or a prostate cancer, that primary tumor actually is not the actual problem. Because a primary tumor, the surgeon can cut out. The problem arises in cancer when that primary tumor starts spreading around the body. So that is what we call metastasis. Okay, and that is what we're trying to avoid. The primary tumor can be treated with what we call curative intent. So that is a combination between surgery, sometimes radiation therapy, sometimes drugs, but for all intents and purposes, we can cut it out. The only time that a cancer really becomes a real problem is when it spreads to other parts of the body. So the way this happens is that cancer cells and other parts of the primary cancer start spreading through the blood. How long does the blood take to circulate the body? Want to take a guess? Got 1 minute? Other bets? How long does it take heart to heart? The minute is about right. It's kind of interesting. When I cold call people and force people to answer, it's kind of funny because you get a huge range of answers. And 1 minute is about right. So now think about every time that a cancer cell actually leaves that primary tumor site, wherever that is, within 1 minute, that cancer cell will have seen, roughly, the body. Okay, so the exposure is huge. So the fact that metastasis actually does not happen very often is actually pretty amazing, okay? So we have to think about that. It's a really, really hard process to be successful. So how do we start studying that process? So again, this is not something new. Thomas Ashworth, an Australian physician, discovered this process first in 1868. Okay, and this is when he first looked at a at the time, of course, there was no photography, so they drew these pictures. When he looked at an autopsy sample of a patient who had died, and he looked at the blood that he had spread over a glass slide, and he found cells that were consistent with those of the primary cancer. So this is how old this field is, right? And we still haven't solved it, right? Quite interesting, actually. It's an obvious problem, but there is just not necessarily an obvious solution to that. I'm just throwing these up. These are Kaplan-Meier curves, survival curves, that essentially show that if you have these circulating tumor cells, and this is now data that was published 20 years ago, if you have these circulating tumor cells, if you have more than 5, your likelihood of survival is significantly reduced over when you have less than 5. Okay, this is just to say nothing else, but we can use these cells as biomarkers. What has happened since then? Oh, yeah, this was kind of fun. So this first paper was in 2004. When we started working in that space in this 2002-2003 era, we started asking the question of how do we go from Thomas Ashworth actually drawing that picture to us being able to talk between pathologists, physicists, physicians, and patients. And we built a tool set together with a team from Microsoft. And it was interesting because this was never intended to be up on a keynote with Steve Ballmer. But this was actually one of those very fun events when as a physicist you get to go up on stage with somebody like Steve, who is actually incredibly smart. and incredibly geeky as well when he is, outside of the show business, so to speak. But this is when we first started building new tools and new technologies that really enabled us to work together across disciplines. And so the reason why this has taken so long for us to figure out is that these cancer-like events in the circulatory system are incredibly rare. So this is a needle in a haystack problem. So white blood cells, you have a couple of thousand per microliter of blood, and these circulating tumor cells, you only have a handful of them per milliliter. So it's 1,000-fold more complicated to do. And so we always equated this to the Where's-Waldo problem, and what's depicted up here, the idea is really that this is a glass slide that can hold about 3 million white blood cells, and what we are curious about is whether or not there's 1 or 2 cancer cells amongst them. So in many ways, it's just a super high-speed Where's-Waldo game, and of course, almost screams deep learning model as far as really trying to figure out how all of this works. When we did this in the beginning, of course, it is finding the positives is just as important as finding and characterizing the false positives, because the way you reduce the false positives is actually by learning about the false positives themselves. So anyway, so we did that for the last couple of years with various iterations of algorithmic developments, and we are still far from done with this, because again, this is one of those really, really complicated issues. We have been building generative AI models now for the last 18 months, and this is how we believe we're actually going to make progress on this. I want to be sensitive to time because we have a few minutes for questions as well. What is fascinating is that, of course, our goal is to diagnose cancer just from a blood draw. So this is super interesting because, as I mentioned, right, this is when cancer cells leave the primary tumor, circulate through the body, and eventually cause metastasis. One could argue that once that happens, it is too late. 20 years ago or 15 years ago, we always argue that this is not for early detection. But when that happens, it's actually too late. What science has taught us in many ways, in surprising ways, what science and the evidence has now shown us is that, in fact, we can find early indicators of cancers in the blood. And this makes sense as well when we start thinking about the blood. It's not just when we think about blood, it's like, well, it's a blood test, it's a blood sample, etc. But it's really your immune system, right? And of course, no matter what happens in your body, your immune system has actually clear knowledge of what's happening in your body. Because cancer doesn't show up overnight, even though seemingly it happens overnight, but it actually doesn't. It takes years to develop. Why does it take so long to develop? Well, because your immune system actually keeps it in control, it keeps it in check. So there's a long period of time within which there's a balance between the evolving cancer and the immune system. And that means we just have to figure out how to actually read that out. And that is the process that we as a field are in the middle of right now. So I'm getting a little slow here. I want to get to, let me go back here. So I just want to point this out. So this is sort of like where we are currently at. The blocks here, left to right, is always late-stage cancer, early-stage cancer, and normal. And each of these colors is essentially a different cell type that is significantly different in the circulatory system, in the blood sample itself. And we are currently we are in the middle of trying to figure out what each color means in terms of its underlying biology. So we are now able to find these cells. We are able to figure out which cell type makes a difference between late stage, early stage, and normal. And now next up is to actually understand the underlying biology to then refine the process. And this is what we mean by augmented intelligence. The reason why this is, of course, so important is that when we diagnose cancer, and it doesn't matter whether we look at US data or global data, the most important part about diagnosing cancer is, of course, diagnosing it early, because when I diagnose it early, prior to it having had a chance to metastasize, I can treat it with curative intent. We see this by looking at the 5-year survival data, where localized, meaning early stage disease, has a 99% survival rate. And that, of course, that drops down to 30% in patients who are being diagnosed with late stage disease. So the idea is, of course, that to never let that happen again, right? Get to a place where we can actually do this for all patients when the disease is still localized. This is complicated, though, because this is a good example. This is mammography, just looking at screening data. So on the left-hand side, is 1,000 women who were screened by mammography and with a 10-year follow-up. So over a 10-year follow-up period, you end up with 5 women dying from cancer, 16 women dying from other cancers, not breast. When you look at, this is without screening. When you look at with screening, you save 1 woman, right? So you have this significant improvement of 20% of reduction of breast-related cancer deaths. But coincidentally, of course, you end up with 1 more woman dying of different cancer. Okay, so that is where it gets complicated. Now, this does not mean that screening doesn't work. It just means that we're not good enough. We know that with screening we can reduce cancer-specific mortality, but we are just not good enough yet to actually do this in such a way that it saves all the lives we want to actually save. Let me go through this. The other part, of course, is, or the reason for that is that while mammography is something where squeezing a breast between 2 metal plates and then taking an X-ray is not really something that anybody would ever look forward to. So it by itself as a method, it seems to me a bit arcane to start with. But the real problem is that we end up with an overall accuracy of only about 85%, and that means that we end up with a huge number of false positives and a significant number of false negatives, and that is what again leads to that limitation of the effectiveness of breast cancer screening today. Now, of course, we as a field, we are using AI methods right now because again, it's just another image to actually improve the accuracy of this. But of course, the obvious statement here is that we want to use a blood sample as a complement to that, right? So that we actually have women with, so for example, women with dense breast tissues. And that means that pretty much the majority of women under the age of 50 have dense breasts. So these are breasts that are still very active. That is not just smooth fatty tissue. So for those women, as you can imagine, if you have highly structured breast tissue still, it is much harder to find an emerging cancer within that. So again, for those women, it makes a lot of sense that actually a real solution would actually be a blood-based solution on that. So I'm sorry, I'm in part still suffering from the PowerPoint hiccup. I want to show data from colleagues of ours at Grail, a company in the Bay Area. And again, same idea, you see these pictures, these are their slides now. But again, the same idea as what I showed you before, right? It's that primary tumor, that's not the real problem. The real issue is what actually goes into the circulatory system, different ways of identifying it. And the amazing part here is that they are actually also not looking for cancer-specific mutations, which is what we all did 20 years ago. When we first started realizing that cancer has very specific mutations that we can identify, the obvious thing to do was actually to look for these mutations in the blood. That actually does not work for early detection at all, because that signal is too low. In fact, what they are doing, and many others are doing, is to look for what we call methylation patterns. So that is a different modification to the DNA, and it essentially tells us that there are fragments of DNA in the blood that are coming from a tissue that shouldn't be there. Okay, so it's super interesting. That could never be done. This would be impossible to do with anything other than deep learning classifiers. Highly underappreciated because they really don't talk much about it, but that is one of those fundamental breakthroughs really truly enabled by deep learning methods. And what's been really amazing is that they have been able to do early detection on a very large number of different cancers and be quite specific about the origin of that cancer as well. And there's a lot to talk about why the specificity has to be so high, which is super important. But this is particularly important for all of those cancers that currently do not have a screening method. However, the limitation of that is that when you look, for example, at breast cancer, where we do have screening methods, and I just complained about the 85% accuracy, so they end up with a sensitivity of only 30%. makes sense for a number of different reasons, but of course this is completely useless. This is highly ineffective in the clinic to screen for breast cancer. Okay, so the risk now here is the concern of AI, right? The risk here is that women will do this test, they will be negative, and they will feel confident that they're cancer-free, which they should for all of the cancers that are over here on the right-hand side, right? But it should not replace their mammogram today, and it should certainly not replace a future breast cancer-specific blood test, as there are a number of them are evolving right now. So this is the tricky part of just how do we start thinking about behavioral economy, really how do people perceive their risk, and how do we deal with these new tools as they're emerging. So with that, I am closing, I'm going to close this and then open for questions for a few minutes, is that these deep learning methods, everything that we have seen around AI and as it is evolving, as it's going hand in hand with better and better molecular methods, again, this does not happen in a vacuum. This would never be possible if it wouldn't be for all of the genomic and proteomic and imaging methodologies that are developing all at the same time. But with that, what is ahead of us in terms of early cancer detection, and that is just the first disease. This will happen with all of the other diseases, all of these big chronic diseases as they're coming. It's just absolutely striking. And what we really need to figure out, what is it actually that's worthwhile doing? So the healthcare economy, I think, is going to be, the healthcare economic models are going to be really important because these experiments are expensive. They take very, very large sample sets, very large clinical trials. And it's a huge investment of time as well in terms of the individuals who are working in that space. Beyond 2024, I do think that we have a real opportunity across the disciplines. This will only happen if all of us actually learn how to really truly work together to really solve some of these big problems in society. So with that in mind, and the reason why we always talk about this in the context of convergent science, pick a problem that deeply interests you, because it's a huge investment, it's really complicated. Figuring this out is really hard, takes a long time. Develop the deep knowledge about the problem itself. This is not your discipline, right? Remember, a problem in society, right? I'm a physicist. I am not a cancer biologist. This is not how I grew up. I grew up as a physicist. But there ended up being a problem that just deeply impacted me, that I wanted to really understand better and see whether or not I, as a physicist, can actually contribute to the solution of that space. And then picture the exact patient who you want to help. If this is in medicine, this could be something else. It could be the planet. It doesn't matter what it is. But truly picture what that actually means for you as a person. And then just go ahead and do it. It's just like you guys showing up here today, right? It's just a matter of just showing up and starting to work on that particular problem, which again, I think to me, this is probably the most important part. To me, this was, of course, motivated by my mom having breast cancer. It's very simple. And so this is how I went down that list, where I said, okay, as a physicist, what do I do? And then I started realizing that, yes, in fact, we all can. So with that, a quick thank you to my own research group at the USC in Los Angeles, to our patients and their families, our funders. This is why this work is so much more complicated than doing this in mice or in cell lines. People had warned me from the very beginning that, Peter, this is crazy, don't do this in humans, this is too complicated. Human individuality is, the diversity of human individuality is striking. But again, I think we have a real opportunity, and I think also a responsibility to actually figure out what disease means in humans and not just in mice. But with that, I do think that digitizing cancer as that step of understanding the disease itself has a real chance at making a difference in the world. And with that, I would like to close. Thank you. And I guess we have a few minutes for questions.
Thank you, Peter. Questions?
Maybe I would like to ask, maybe specifically for the cancer research. So you said that, well, of course, where everything starts and ends is the availability of data to actually train these models. What is the situation right now in cancer research? Are there any, perhaps specifically in the US, efforts to kind of collate data across many institutions and make them public, so anybody who is good at AI can actually help? Or is it still silos and silos?
So here's what's complicated. There are lots of efforts going on, but in every one of these efforts, right, it requires the data architecture guys, together with the data science guys, together with the clinical practicing guys, together with the clinical research guys, together with the clinical administrators who control it, to actually figure out, what does that mean? What kind of data? Because it's garbage in, garbage out. The reason why we have big data is because we don't have good data, right? There's all of that. It's really hard. And we try this at our own institution, and I think this is a real opportunity for you here as well, right? Because you live in a world where get together with your colleagues over in the Faculty of Medicine, right, and figure out how can we actually get data sets. What does that mean? Is it X-rays? But X-rays by themselves are not good enough, right? Because you need a clinical annotation with it. Even in the clinic, that lives in a totally different world. That might still live written down on paper somewhere. So these efforts are super important, and I think they will get accelerated by developing small pilot projects and figuring out what is it that's a potential question that we want to answer, and then just starting this is what I think by prg.ai and efforts like that start that conversation. So definitely still at the early stages. That's why a lot of the papers that you've seen, these breakthrough papers, are coming from places like Mass General Hospital and other places where they have had a decade-long investment of putting these data sets together. Probably, I think, one of our biggest challenges as we go forward.
And probably AI can help in the process itself.
Oh no, absolutely. So absolutely right. We are because you need to identify the problem, identify the question, figure out who are the people, who are the players in that problem, and then just start putting it together. And the ability for computer science today to actually develop these algorithms, at least in prototype fashion, fairly quickly, is a huge part of that. Thank you.
Thank you for the answer. Another question, please. I have a question. You mentioned 2023 was an important moment for AI coming out. When do you expect next important moment, such a breakthrough or?
Oh, at the same level, I don't know, because that doesn't happen very often. But I do think what will happen next. Between now and 2025, I believe that in radiology, so everything that has to do with X-rays, AI as a companion, as a co-pilot, will be everywhere, in the clinic and approved. Truly approved in the US by the FDA. What the European approvals will look like, we'll see. It will be absolutely critical that these algorithms go through the same rigor of regulatory approval. So this is going to be another huge problem, right? Because in computer science, we are used to conference proceeding papers every 3 months, right? And all of a sudden, somebody says, no, actually, you need to have a 10-year outcome on a clinical trial. Okay, so that's going to be super hard, because all of the computer scientists are going to be like, well, my work is done. I should get the fame now, right? I should get the paper. This needs to go into the clinic. No. Right? You actually have to have that follow-on. So that's why these regulatory approvals are incredibly important, because remember, we are making life decisions with these algorithms, right? This is not just what kind of shirt am I going to wear next week or any of that, right? These are truly health decisions. But these first approvals are in the middle with the agency to make their way through. So I think over the next 12, 18 months, all of radiology will have AI as a co-pilot with regulatory approved algorithms. I believe the next breakthrough in terms of early cancer detection, I think we will have, it's 2024, by 2028, I should never put dates down. That is such a terrible idea. By 2028, I believe that early cancer detection using blood-based approaches will be in common clinical practice. And the breakthrough will actually be for us to understand the relationship between the cancer and the immune system, and recognizing that, of course, the blood is our immune system.
Good time for the follow-up Body and Soul conference. Yeah? Any other question? I still have one in my pocket. Any other question? If not, then my last question is, when do you expect that AI will get the Nobel Prize?
So it'll be interesting, right? Because we also have, there are really interesting efforts going on with green AI now. Because of course, if you look at the carbon footprint of training GPT 4.0, it's quite striking. So there is lots of innovation that still needs to happen on the computer science side to actually enable next generations of AI. I do think it's at least another 10 years out in a world that is going to look very, very different from where we are today.
I am happy that I will be retired by then. Thank you very much, Peter. Thank you.
Thank you.
Do we need a short break? Or can we continue right away? 5 minutes break. 5-minute break. There are restrooms here and restrooms in the back. physics. Let me just briefly introduce him that he got his master degree from Kansas State University and Faculty of Mathematics and Physics, his PhD, and that was in what? Edinburgh was PhD in neuroinformatics. Yeah. But the first master degree was in computer science, right? Yeah. And he came to Faculty of Mathematics and Physics a couple of years ago with the project Primus, and his group is called Computational Systems Neurosciences Group. Correct? Correct. Please, Jan, the floor is yours. You may use mine.
Okay, sorry. And may I please have the point? Ah, it's over there. Okay. So thank you. Thanks a lot for the introduction. So when we present a visual stimulus to the brain, we will get a pattern of activity appearing in the brain. And if we switch the stimulus, a different set of neurons, a different pattern of activity appears. And it's basically the basic foundational dogma of sensory neuroscience, and an idea on which we will be basing everything we will talk today about is that it's basically that pattern of activity in the brain that encodes the visual stimulus that we are seeing. And so the idea is that if we can, for example, artificially recreate that pattern of activity in the brain, we might induce the perception of that stimulus. That's kind of the basic idea around which everything I will talk about will revolve. Now, in the last 10 years, there has been a great developments in terms of the technology which allows us to communicate with brain, both in terms of writing into it and reading from it. And one of the probably most tantalizing applications of these new technologies, these brain-machine interfaces, is for remediation of loss of vision or motor function. Now, the specific use case we will be talking today about is the loss of vision. So we have around 15 million blind people around the world. In most cases, the issue is directly in the eye. And now the question is, how can we potentially help them? And one of the avenues is to use exactly these kind of brain-machine interface technologies to basically bypass the broken eye, let's say, and reintroduce the visual information further down the visual processing pathway, essentially directly into the brain. That's what we're going to talk about. Where in the brain? Well, probably the best area to do this is primal visual cortex. It's in the back of our head. It's also called V1. I will refer to it like that for the brevity. And it's the first cortical area which processes visual information, and it's also actually the largest and most well understood visual cortical area actually in the brain. Now, how would such hypothetical prosthetic system work? You would probably have a camera which will be recording the world in front of you. The images from the camera would be going into a processing unit where they would be translated somehow into control signals for the implant, which would be actually sitting on top of your brain and activating the brain. Now, hopefully you can appreciate that this is a very complex problem which requires multidisciplinary sort of collaboration. You need engineers to build the hardware, you need neuroscientists, surgeons, even computer scientists. There's one particular problem in this puzzle that we are interested in, and I'm going to be talking about. So essentially, imagine you actually even have that system, that physical system in place, and you can use it. There's a still question, how are you going to use it? So essentially, as I already said, visual information comes into the brain and elicits some pattern of activity in V1. Now, in the prosthetic situation, the information comes into the goggles, and now we need to translate that information into some kind of signals for the LED array, some instructions, to the implant, which will then elicit some other pattern of activity. And of course, the idea here is that we need to the closer we can make the pattern A and B, the more likely we are able to elicit the percept that we are seeking. And so the question is, what is this translation? What is that function F that translates visual inputs into those instructions for the signal? Essentially, what should be the software running on the or stimulation protocol running on the implant? And that's the question we are trying to answer here. Now, you can probably
appreciate that the answer to this depends crucially on the coding that the V1 does. How does it encode visual information? And so before I can tell you how we want to solve it, I have to give you a very quick crash course of the coding in primarily visual cortex. So let's do that. So probably the best way to understand how neurons in V1 code visual information is to explain the concept of receptive field. So if you have a neuron here which has this receptive field, and this is kind of the typical shape of receptive field in V1, what we mean by that this neuron likes dark stimuli here and bright stimuli here, and it doesn't care about what's in the visual field anywhere where it's gray, anywhere else, okay? Now, these receptive fields of neurons in V1 look like that. They can be differently oriented, they can have different positions, but otherwise, they look kind of like that. It's a bit of a sketch, of course. Nevertheless, the consequence of this particular shape of this receptive field is that if we take a white bar and present it to such neuron, and the white bar nicely aligns with the receptive field, the neuron is going to respond a lot. And if the bar is of a different orientation, it doesn't align with the receptive field well, the neuron is not going to respond. So essentially, what we know, what is one of the main hallmarks of the coding in visual cortex is that neurons are basically edge detectors. They like to look for borders between objects about edges. That's the most important aspect of the coding. Now, what is also important for us today is not only what individual neurons code, but also how is this coding organized across the whole cortical area. And there are two main principles I still need to explain you. So the first one is so-called retinotopy. So as I told you, different neurons in the cortex have receptive fields in different places. But if you would actually blow up the cortical surface and now start and go across it, we would see that as we are moving through the cortical space, the receptive fields are also slowly moving smoothly, meaning basically there's this mapping of the visual field, of the coordinates of the visual field onto the cortical surface, okay? And the same thing essentially holds also for this coding of orientation. So if I were to actually record the orientation preference, the orientations that the neurons like across all the cortical surface, and encode them, or color them by this color code here, then we would get these beautiful so-called orientation maps, orientation preference maps. And what they basically tell us is that if we have few neurons which are next to each other in the same kind of color in the same orientation domain, in this is a colored area, we will find that all those neurons will have receptive fields in the same place and of the same orientation. Now, if I move just a little bit further, the neurons will change the orientation, but remain roughly in the same position. And if I move even further, neurons will change their position and orientation as well. Okay, so this is the principles. These are the two main hallmarks of coding. Now, it's very important to explain at this moment that there's definitely a lot more to it, but these are the kind of main two pillars of coding in V1. Now, how does this now relate to how the vision prosthetic systems work currently? Now, I want to emphasize all of this is entirely experimental. It doesn't work well essentially yet. However, the current systems are based around an empirical finding that if you take an electrode, you stick it into the cortex and you activate it, the person will see a little dot of light which corresponds, and the position of that light will correspond to this position in the retinotopic mapping that piece of cortex you're activating has, okay? Now, the idea basically now is that we can have many of these electrodes, we can induce many of these dots, and if we have a stimulus, like this A, for example, we will recreate that stimulus with these, in these dots, and that's how we can try to kind of give some basic vision. Now, there are at least two important things to say here. The first one is that, okay, these systems don't work very well yet. We, for example, have a trouble putting a lot of electrodes in the brain, but also, even if they worked very well, we can imagine that we cannot get a very high quality vision out of this type of approach. And also notice that basically what this approach is doing, that it's only relying on this coding of position and completely ignores this coding of orientation, okay? And this is exactly where we are coming, so I'm finally coming to what we are doing. So basically, our goal is to find a stimulation protocol for this type of systems, which will not only take into account the retinotopy, but also this orientation preference. Now, there's one last very, very important thing I need to explain to you. It just makes sense that if you want to use or engage coding under your implant, you actually need to know what it is. You need to know which neurons like which orientation and position there. This is actually very difficult to find out, but we can hope, the best we can hope to find out under the implant is these two information, the orientation and retinotopy. None of the other aspects of the coding I didn't talk about, but they exist. Okay? So this is both, our goal is both use both these information, but it's also a limiting factor. We cannot assume we can have any other information about what these neurons do underneath our implant. Only these two information. This is very important to understand what's going to come. So as I said, our goal is to come up with a stimulation protocol which uses information about the orientation and position and nothing else. Okay. So finally, how do we do this? A quick check on time, okay. Here I just want to give a shout out to Luca and Martin who have worked on this and did most of the work. And here's our solution. So as you can probably anticipate, the answer is machine learning or some form of AI. So we're going to try to learn this coding from data. Now, what will the data look like? The data is about thousands of images which have been then presented to macaque monkeys in which hundreds of neurons were recorded. That will be on the output of this network. We will have these neurons which we will be trying to basically predict. So hundreds of macaque neurons were responding to thousands of images. Now, what I will show you is that we will be using the model to train it in a one way, and then to use it as the stimulation protocol, there will be slightly different ways. So at the top is the training, at the bottom is the inference or the usage of the model. So the model is consisted of multiple layers of these so-called rotational equivalent convolutional neural layers. Those who know what convolutional neural networks is, the rotational equivalent CNNs are the same thing, except they are also convolutional, not only in position, but also in rotation. Okay? So basically, these different colored layers correspond to these different rotation channels, essentially. And so we have multiple layers of this. And then the important trick is the readout. How do we read out from this common rotational equivalent core? And so the way that we do it is that we say that for every single neuron, we will allow only one position and orientation that that neuron will be allowed to use out of the core to predict its responses. For every neuron, it can be something else, but for every neuron, it's going to be one position and one rotation. And so if you think about that, this is what embodies this constraint we have, that all we can know is the position and orientation of the neurons. We are telling the network to find the best common mapping for all these neurons, where the only thing that can be changing between these neurons is this orientation and position. So we're going to train the network this way on this macaque data. And what we can then do is to reuse this common core to predict the responses to a new natural images to neurons to neurons, for example, in different animal or even in a different species, let's say in a human in theory in the future. Now I will remind you again, our assumption is that we know what the coding under implant is. We know these positions and orientations. And so we're gonna the way we're going to set it up, that we will now have a new readout where for a given neuron that we want to predict the activity, how strongly we want to activate it, we are going to use the readout from that specific position and orientation we know for that given neuron under our implant, okay? And this is going to basically give us these predictions of how to stimulate under the implant, and that's essentially our stimulation protocol. Now, how much time I have? Okay, great. So this slide is here. Just a big shout out to Andreas Tolias, who very kindly provided this macaque data. And the next thing I would like to show you is basically how do we do, show you at least some numbers. Now, before I do that, I need to do one last little detour, which is that as far as we know, we are the first ones who are trying to develop such a protocol with this kind of constraints. And so we don't really have a good state-of-the-art. Nobody tried this before. Luckily, there exists this very standard canonical model of V1 cells, which is called energy model. It's a very simple, sort of completely hardwired, handcrafted model, which basically, in its linear form, it's just one linear filter, which is fixed. It has this, gabber, basically the shape, the shape of the receptive fields in V1. And in the nonlinear form, it has these two filters followed by some simple nonlinearity, and that's all summed up. The point is that you can parameterize these models with just what is the rotation and what is the position of these filters in the receptive field. So essentially, you can use it as a kind of a baseline for what we are trying to do. And so here are some kind of the most important slide, if you wish. On the validation data set, if you use just this energy model, we can basically predict the correlation we get between predicted and actual responses is only around 0.28, which is, small number, but it's not actually trivial given this is a really, really, really simple model of this very complex coding that you have in V1. What is then absolutely the most important, of course, is that our deep neural network manages to increase this predictivity by about 35%. So what this actually means that our network finds some common coding principles across all neurons in V1, which are on top of this very basic model, and that can further help us improve the stimulation protocol, essentially. Now, the last interesting thing to ask also is how restricted we are by this fact that we only can know this orientation and position for the neurons and none of the other information. And so what we can do is basically remove this restriction from our DNN, basically remove this very restrictive readout, let the readout do essentially what you want, combine as many orientations and positions as you want, and see what correlation we're gonna get. And what we see already is much higher number, and this actually tells us two important things. The first one is that, in fact, this is pretty close to state-of-the-art what people can do in terms of predicting neurons from this kind of data. So it tells us that the kind of underlying architecture, AI architecture we are using is decent, it's competitive, but it also tells us basically that yes, of course, there's a lot more to the coding than just the position and orientation, and so that's a very big limiting factor, but basically this is the best we can hope for under the circumstances. That's kind of like, the estimate of what's the best we can hope for is also kind of an important information for developing these systems going forward. Okay. And I will just very briefly explain this one last slide because I'm running out of time. So at this moment, in the ideal world, we would now take this stimulation protocol and actually go and test it in a real prosthetic system. Unfortunately, the systems are still being developed and they are not sophisticated enough to basically test these systems. There are a lot of people working on this. We are part of these consortia, but these systems are not ready yet. So instead, what we did is that in my group, we've been actually developing very detailed, large-scale spiking recurrent models of visual system over the many years. And so we actually use them as a simulation environment, as a kind of digital twin of the visual cortex, and try to simulate what will happen if you use the stimulation protocols in these models. What's important is that in these models we can both simulate what is the response to an image when we show it through normal visual pathway, but also we can simulate this external stimulation actually. And so what you can see here is the visual stimuli that we will present to the model, and this is kind of the prediction of the activation of the cortex that the cortex would have if you would show these images through normal visual pathway. The brightness here corresponds to the activity in the cortex, and we just color-coded these neurons again by the orientation preference, so it's a bit easier to read. And then in these two double columns, we will have two different protocols that we will test. The first one will be just this naive retinotopically based protocol. I say naive, but remember that's what the current systems are using. They are just using the retinotopy. And here is our DNN-based protocol that that I have just explained. Now, this is the activations that these protocols would suggest we should do in order to recreate these stimuli. And these are then the activations of the cortex that are as a result of this external activation of cortex based on these protocols. And hopefully you can just even with your naked eye see that our DNN basically matches the target activity a lot better than these naive retinotopic protocols. And the last slide is just the same thing with slightly more interesting stimuli. Now, I pretty much ran out of time, and so I will just quickly flip to the team slide, let it hang in there, and thank you for your attention.
Thank you, Jan. A quick question?
Maybe just a general question, like regarding the prosthetics development. Actually, I know it's not your specialty, but still will ask, like, how much is the visual cortex actually homogeneous across individuals? Like, because if the structure changes a lot, then it might be problematic to introduce some intervention.
Yeah, so I think these basic principles, this retinotopy and orientation maps, they kind of look the same. So there is a decent sort of homogeneity. However, it's like a fingerprints. Like fingerprints look the same as a pattern, but they are a little bit different in every human. And that's exactly why I was emphasizing that we need to actually know for every specific subject exactly how this map looks like. And we can potentially, this is actually a separate big problem that we are also working and others are working on, but we can conceivably probably figure out how to figure out this orientation and position, which is why we are assuming we know that here, but probably not these other much more finer aspects of the coding, let's say.
Okay, cool. Can I have one more? Yeah. Okay, and what is the resolution of the thing which does the excitement?
That's a very good question. I deliberately kind of didn't talk about it at all because there's not one. There are many different systems with different properties. And I try to kind of keep it general. So these principles I explained are sort of, applicable generally. But actually, it really depends on the system in a sense that essentially systems which would have really low precisions, and a lot of them that are being used now do have, they, let's say, don't have enough precision to really apply what I explained to you. That's kind of true. So in that sense, we are part of big consortia which are trying to develop the new systems. And in parallel, they are developing the hardware, the software, all these different aspects, which is also the downside that we cannot test it yet.
Last question.
So this is fascinating. How do you, what's the difference between a brain, because at some point then you stimulate the brain, right? So you are doing this with the results that you're showing for how we are used to be looking at this.
Yep.
Not how a brain will, because there's going to be post-processing. So what's the difference between a brain of somebody who has been blind from birth, no training, versus somebody who became blind at some point later in life?
So that's a really tricky question because I think underneath it you managed to open like 3 super interesting topics and I don't know which one to address first. So well done on that. Thank you for making it easy for me. But I think kind of the most direct question, which is, so actually nobody at the moment is even thinking, as far as I know, how to return vision to people who are born blind, exactly because none of what I've told you, very likely, we can actually test it, that's the paradox of it, but none of what I've showed you probably is there, or that it is in a very, very basic and destroyed way, let's put it that way. So everybody at the moment is trying to solve the problem of acquired blindness. Luckily, if I can use that word, that's actually by far the majority of cases. Interestingly, not so many like blindness. Yeah, it's mostly acquired either through injury or disease later in life. Yeah, so I'm answering that part of the question, but there are another 3 things I would like to say, but okay, I'll leave it there, I think.
Okay, thank you once more.
Thank you.
So the next speaker will be Lubomír Štěpánek. Maybe ask for the next slide. And by... Yeah. Is this you?
These are my slides for questions, so please.
So can we go on, please? Yeah. This is Lubomír Štěpánek, and you see that he is from Institute of Biophysics and Informatics of the First Faculty of Medicine in Prague. So please, Lubomír.
Okay, thank you much for your nice introduction, and thank you for coming to my talk. So my name is Lubomír Štěpánek, and I came from the First Faculty of Medicine. I also work on some different other institutions here in Prague. And I will be talking about a typical task in a survival analysis, which is event prediction. And this can be done using some very traditional methods like Koch's proportional hazard model and so on. But those methods are typically very limited by some statistical assumptions. And what we did in our study is that we tried to overcome this this limitation of the coming from the assumptions by implement of machine learning methods into the flow chart of the prediction or workflow of the prediction. And we try to apply our methodology on prediction of COVID-19 antibody decrease under the laboratory cutoff, and try to compare the traditional methods with this proposed methods. So we live in a disclaimer time, so there's some kind of, I try to do some licensing. It's like a copyleft license, so we can do almost everything with the slides or with the recording, no worries. So I will talk about, I will start with a quick introduction and motivation, piece of motivation, why this task is important. Then I will revisit the traditional approach, which is usually of event prediction done by Koch's proportional hazard model. And I will try to introduce our proposed method, which is based on time to event variable decomposition. I'm just going to talk about more in details later. And I will try to explain also some details about this. And finally, I will try to apply the methodology on COVID-19 test, as I told before. And finally, I will try to highlight some key findings, of course, and make some outlook. Just a footnote side, of course, it's a big pleasure for me to say this is just a joint work with some of my colleagues from some of the institutions, and I will mention it later on individual slides. So for the very beginning, in survival analysis, what is typical, one of the typical tasks is just the prediction of event. So it means that we have a given individual, we would like to know, and we have some defined event of interest. We would like to know when, for a given individual, whether the event of interest will occur or the individual is going to experience such an event of interest, and if so, then when is going to be registered by the individual. So you can see it's this kind of target variable in a survival analysis typically kind of two-dimensional, because we have two domains: time domain, so when is going to happen, and event domain, whether it's going to happen or not. So what is typical for medicine is just the right censoring. I'm just going to this works in medicine, because typically we have some limited time of our studies. We have some start and end of let's say study time period. And what may happen, for example, is that we may monitor some patients, but the defined time event of interest may simply happen after the end of observation. So what we typically can know, this is a kind of situation that we have no complete information, because what we can know is that it simply didn't happen until the end of the study, but it may happen somewhere whenever later. But this is kind of this is just called censoring, and it's a kind of typical, let's say, challenge which is typical for survival analysis, that we have to deal with censoring. So the methods that are relatively well established in survival analysis are dealing with the censoring, and that's why, since and the sensor gets challenging. That's why it may happen. It happens like frequently that those methods are relatively complex, and since they are complex, they are limited by some relatively tough statistical assumptions. And what we try to do, it's a relatively simple idea. We try to replace those, let's say, assumption limited kind of methods coming from several analysis by something which is not so much assumption heavy. It's almost assumption free, which are typically some machine learning methods. And we try to replace those typical traditional methods by something which is not so much assumption free. Because typically, for example, proportional hazard model is called proportional hazard because it assumes that for every defined subgroup in your data, there should be like a constant ratio of hazard functions across all time points, which is some kind of assumption which is frequently violated in when we try to apply it on a real world data. So that's why Cook's proportional hazard model then may, for example, fail to do the prediction correctly. Aim of the work is just to, as I already told, apply the method on some real world data to do something like a proof of concept, and on a more theoretical point of view, we try to do something like a time to event variable decomposition to time and event component, and employing the classifier, which is usually assumption free. So this is like a, let's say, common scheme of a Cox relation model, which is, let's say, maybe almost 50 years old. So on the very beginning, we have something like a cover rates, anti-cover rates. So on input, we have some variables that may depict the patients or individuals of our interest. Then we apply the Cox regression, and on the output, we usually are able to construct a time-to-event posterior distribution. And if we have this distribution of time-to-event variable, it's relatively easy to calculate for a given time point and given individual what is, let's say, a probability of experiencing the event of at a given time point, and so when and whether it's going to happen. So this is something which is, there's nothing new about this. There's some mathematics, but we can simply omit this because it's just an illustration of that there is a well-established theory behind this, and it's well established in the community of statistics and survival analysis at all. So if you would like to try to reuse the Cox proportional hazard model as a classifier to make it comparable with our proposed method, we simply start with a survival probability, which is probability not to register the event of interest up to some given time point, small t, and whether it's going to be this survival probability, let's say, large enough, larger than some p-threshold, but it's closely to situation that the event of interest simply doesn't occur before time t, and vice versa. So this is a relatively easy way how to let's say, refine the Cox proportional hazard model as a classifier. Also, we may simply skip this mathematics, but there's nothing new about this. It is not rocket science at all. So what is like a piece of novelty in our study, and what we try to do is like to replace the Cox model by something which shouldn't be, let's say, so much limited by statistical assumptions, by the proportional hazard and things like this. So we try to employ a machine learning based classifier into the workflow, and because we know that the time to event variable is kind of two-dimensional, because we know that there's a time domain when it's going to happen, event of interest, and whether it's going to happen at all. So we decompose the time to event variable to its time component and event component. While the time component becomes one of the covariates on input, the event component is now treated as a target variable for the classifier. So the classifier simply classifies into two possible categories of this target variable, whether it's going to happen or not going to happen, considering that the time component is used as one of the, let's say, explanatory variables. So this is like a paradigm switch, and this is what is new in this approach, let's say. So as a classifiers, we used, let's say, two families of classifiers. Those classifiers are usually, let's say, traditional, I would say. There's also, many of them are, let's say, about 20 or even more years old. We tried to, what is nice thing about this, that for example, we can, in the workflow, you can simply replace one classifier that, for example, doesn't perform well by another classifier that performs better, do the classification better. So we tried to compare various classifiers. The first three, like logistic regression, naive Bayes classifier, and neural networks come from a family of, let's say, classifiers that typically use maximum posterior principle. It means that they try to model somehow the final chances or probabilities of classification into a given class, and those chances are compared, and the class that simply got the highest chance to be classified into, this is the final class that we classified, the classifier classifies into. So we have only 2 classes here, even is going to occur or even is not going to occur. And we also used, let's say, more separating, separating classifiers so that supervector machines and decision trees and random forests belong here. And those typically separate the universe of all the predictors into some regions, disjunct regions, so that all those regions should belong particularly to one or another class. And by this relatively easy scheme, the classification is done. So there could be some kind of voting scheme in case that there is more than only one model, and the final class is just the class when, so that the maximum proportion of all the models classify into. What reviewers liked about our work was that this may be a kind of footnote and not so much important for the storyline of this study, but we proved that the workflow is relatively fast, and it cannot be much improved within the domain of time, because we simply prove that time complexity of all the workflow is as fast as the classifier is. So we cannot replace the classifier, so we cannot do it much better. So there was like a formal proof in the publication I mentioned before. And if you just move to the application to COVID data, so we tried to apply our method to COVID-19 data. It was like so much. It's not like large data, but not so small, considering it comes from medicine. It was like 663 individuals, described by 34 clinical and laboratory variables, including some immunology variables. I'm just going to take a look into what variables we used. And of course, I want to mention and thank all the guys from the Department of Occupational Medicine from Univerzita Karlova, because they maintain the data set and collect the data set, so all the credits go to them, of course. If you can see, if you just take a look in the table below, we can see it regarding the IgG antibodies. Unfortunately, it was like a heavy censoring included, so it's more challenging to use only a limited number of data. But regarding the IgM, it was a bit better. But this is like a normal situation we have to deal with, because the censoring is something which is typically presented in several kind of data. So yeah, it's a kind of incomplete situation. So particularly within the first line, you can see the sensor data were like the vast majority of all the data. So we have to deal with it, but the method can deal with it. Just a quick look into what variables were included in the data set. So those are continuous ones, typically some biometrical ones like age, weight, height, body mass index, some blood levels of antibodies, both IgG and IgM, a total count of COVID-19 defined symptoms. This means that this is just those very well-defined symptoms used by WHO or CDC defined in COVID times. It was like popular in those times, well-defined and and strictly monitored, like cough and subfebrile and fever and loss of smell, loss of taste, and things like this. Time between beginning of the and end of COVID symptoms, of course, and what is important for us is the time domain is like a time between laboratory-based proof of COVID-19 and antibody blast testing or sampling in days. Yeah, and the categorical variables in dataset are just those. So majority of them are just, let's say, onset or presence of a given symptom, like where there's like a muscle pain or fever or something, and things. So those are the defined symptoms. And also, what is important, some gender, and of course the degrees below laboratory cutoff, whether it occurred or not for a given individual. Just to make it, let's say, more reproducible, we applied something which is relatively standard cross-validation. So we simply divided the training data set into two proportions, 90% to 10%, and within each iteration we estimated the, let's say, performance metric on a given 10% and trained the model on the remaining 90% of the data set. So we calculated accuracy, precision recall, and F1 score, and averaged them across all the iterations to get more robust point estimates of those metrics. So those are the results we got. So maybe I will just start with the table below, because IgM and antibody decrease predictions may be not so much important from clinical point of view, because IgM antibodies are more like memory kind of antibodies. So it's pretty hard to predict them, or maybe hard to predict them because of the fact that there could be some subclinical hidden reinfections. So what we simply cannot know about, and that's why you can see that both the Cox-Proportional hazard model and our various employed classifiers are not so well at all, because the predicate accuracy and other metrics are, let's say, somewhere about 50 to 60%, which is not good at all, of course. But what is much more important from clinical point of view is IgG antibodies and their decrease, because those are typically the antibodies. IgG antibodies are those that protect against COVID or manifesting COVID. So their prediction was relatively good, both by Cox-Proportional hazard model, it's a traditional approach, and our approach sometimes, if I just talk about accuracy, outperformed the Cox-Proportional hazard model, because some of the classifiers like supervector machines or random forest and maybe some others have higher predictive accuracies than Cox-Proportional hazard. But of course, it also depends on some imbalances in the data set. So sometimes we are more interested in precision or recall. It absolutely depends on the fact whether we are more afraid of false positive or false negatives. So sometimes it's called that the most important measure about or which is calculated is like F1 score, which is in fact an harmonic average between precision and recall. And you can see that both Cox-Proportional hazard and some of our algorithms like random forest classifier and supervector machines, let's say, perform relatively well. Their F1 score is like larger than 90%. So some of the, let's say, chosen classifiers, let's say, are relatively usable in this manner, let's say. And just to conclude this up, just trying to do this. Yeah, I'm sorry. Okay, I'm sorry. Okay, so I'm trying to. Okay, this is my last slide, but I'm just trying to talk to the microphone directly. Okay, so hoping that at least something will be heard. Okay, just to conclude, so we can use Cox-Proportional hazard model to do some event prediction, but the Cox-Proportional hazard model is relatively limited by some assumptions coming from a statistical theory. So we can try to what we tried is just to overcome those limitations by implement of classical classifiers into the workflow. And firstly, before it, we just simply decompose the time to event variable to time and event component. And as we have seen, it works somehow. Relatively, those the traditional methods and the new methods are comparable. The proposal method is comparable to Cox-Proportional hazard model. But what is an advantage of our method is that it's almost assumption free, particularly for the separating classifiers like random forest or supervector machines. It is relatively fast, so it's not like training. It's just limited by training of data. So if the data are not so large, the training is pretty fast, and it can be used on a real-time prediction. And some, let's say, outlook to some clinical practice. Let's say if you are able to early predict antibody degrees, which can help us to identify patients that are at risk of seronegativity. Those are, for example, candidates to be vaccinated at first in some scenarios, like if there will be just COVID-19 new pandemic incoming or something like that. It's of course applicable to larger, let's say, family of situations of other infectious diseases and so on. Okay, so thank you for your attention. If there are any questions, I can try to answer them. Okay, thank you.
Thank you. Yeah, questions? We have time for questions. Peter. That means the last question.
Really quick though, wasn't it surprising that the models actually did not perform any better than the standard Cox?
I'm sorry, can you repeat it first?
The models, none of them ended up performing any better than the Cox.
It depends on the metrics. It depends on the metrics.
But for all intents and purposes, we'll call them the same. There was no improvement over the
if you are talking about
Cox hazard ratios, which is a bit surprising, right? Because this issue of censored versus uncensored data is huge, but so you can't really extend.
There was no clear winner. For example, if there was no model that would be just absolutely better than Cox model, for example, within each calculated metrics. But we believe that they are comparable. But of course, if you have just one data set, regardless of whether it's large or not, if not a proof of concept whether it will work on different data set, But still, we believe that let's say the Cox model could fail if there will be like a large imbalances, or let's say violated proportional hazard assumption. So this is like maybe the advantage of the proposed method, but yes, you are right. There was no like a clear winner within this. Yeah. Maybe on some different data set it could work even better, but yeah, we simply tried this approach. Whether it will work or not, it's comparable to existing method, but assumption free. Yeah.
Thank you. Thank you again.
Thank you much.
And the next speaker is Martin Scholz from the Faculty of Law and rightfully from the Department of Medical Law. So he will tell us about applications of artificial intelligence in this area, I hope. Yeah? Please, Martin.
Thank you very much for the invitation, first of all, and for everything. So this presentation will be more of an inspiration, perhaps, to ask questions and to discuss and ponder on the regulation of AI than some ready answers. And I believe we are now standing at a point where we can expect a literal wave of special regulation of AI, especially in certain areas such as healthcare. And I would like to offer you some thoughts to ponder on about what would be the best or at least a good approach to this regulation. I think I don't have to explain in this room what is the potential of AI in healthcare and what are possible applications of AI in healthcare. It can be like almost anything. It can be embodied healthcare, like healthcare robotics. It can be diagnostic systems, clinical decision-making support systems, telemedicine, and so on and so on. Sometimes we have even come to quite bizarre results or outcomes. Perhaps you have noticed this study where an AI diagnostic system or radiology system was able to predict the race of patients, and no one knows why. No one has a clue why. Even when taken into account possible compounds like the hospital, the severity of disease or the diagnosis, no one knows how is this possible. And we have also the first fully automatic robotic operation, but it's on a pig, it's not a human over there. And sometimes even large language models are evaluated as better advisors for patients than actual physicians, even though this particular results are quite extreme. But we have more examples like this. And just now in April, the first study was released that provided an evidence of an AI system actually saving lives in clinical settings. It was an electrocardiogram system that identified patients with a high risk of mortality, and it just informed the physicians about this high risk, and it reduced mortality by 31%, which is quite a good outcome, isn't it? So, just 2 days ago, the European Council approved the AI Act, the regulation of AI. And I think this is quite a good example of where the regulatory efforts might go, at least because European Union, if the EU is a leader of something in new technologies, it's regulation. We can just think about it what we want, but it's true. And this is the first almost all-encompassing, comprehensive, overarching regulation of AI in the world of this type. And what is interesting about the AI Act is that its approach is based on classifying AI systems based on the risk they pose to individuals and society. There are systems that are deemed unacceptable, or the systems with unacceptable risk, which are prohibited, and there are high-risk system, limited risk, or minimal or no-risk systems. And for each of these high-risk, limited risk, or minimal risk systems, there are different obligations set for the providers and for the deployers. So this is just a wall of text, so we don't really need to read it all. Unacceptable systems, for example, real-time remote biometric identification, but this is prohibited. What is more important or interesting for us are high-risk AI systems, which are medical devices, according to European regulations, medical devices, and these weeks, some first, or these months perhaps, some first AI models were certified as medical devices. For example, in the Czech Republic, we have one AI model named CareBot, which has been certified as a medical device. In the US, there also arise first AI models that are certified as medical devices, and then also some other other AI models. For example, those which will be used to assess eligibility of patients for healthcare or for particular healthcare plans, or AI systems intended to evaluate and classify emergency calls, or triage AI systems in hospitals. These all are going to be high-risk systems, and this regulation will apply to them, to the medical devices in something about 2 years, and to the others in something about 3 years from now. So we can see here some examples of the obligations that deployers have. Deployers are those who actually use these AI systems in provision of healthcare, in our case, such as effective human oversight, monitoring of the operation, automatically generated logs, and so on, and some obligations of the developer, such as high-quality data sets, which can be quite obvious, but it's particular obligation, human oversight measures, clear and adequate information for users, and similar. So this is the approach that the European Union is taking, and in fact, this was a very brief overview, but the regulation is quite detailed. How does the EU do in practice? We can just show many statistics that show our current position in the AI race, if I can say that. And this is just one of them. Private investments in AI. You can see United States, China. When we would count AI startups, it would be similar. The United States, the largest amount of startups, China second. And we can see the United Kingdom. From EU, Germany is first, but you can see that it's not such a great success in this matter. And what do others do? For example, in the US, there is no overarching regulation yet. The AI Act in the EU is really the first one. We can see some attempts to get closer to this overarching regulation, just such as the President's executive order on AI, but it's not there yet. In China, the situation is in a bit similar in this way. There is no overarching regulation, but in the last about 3 years, there has been enacted many specific narrow regulations on AI in China. And what is quite interesting for me, in Brazil, they now discuss a large reform of the civil code, and they want to add a new book in the civil code on digital law. A book in the civil code. Usually civil codes have about 5 books, more or less, and a book in the civil code is inheritance law, contract law, perhaps family law, and they want to add a whole new book on par with these books on digital law. I asked my friends from Brazil who are working on this reform what they think about it. They didn't respond really, but so I'm looking forward to having, I don't know, wine with them sometime and just asking them in person when we meet again. And now what I want to ask is this the right approach? Is this the right approach? Because we are heading for a very complex regulation. And complexity in law is intended to reduce the entropy of the system, to solve the chaos. And it works up to a certain point, but then it arguably makes the chaos even more chaotic. And what I am quite afraid of is that we might be heading to actually increasing the chaos in the system. Because what is the threat of too complex or too detailed regulation? I think there are many. And these are perhaps the most dangerous, in my point of view. Perhaps you can see it differently. One of them is shift of power to non-democratic actors. One politician is often cited with this quote, and often he is cited just as one of the world leaders or something like that, because no one wants to say the name. It was Vladimir Putin who said that whoever controls AI controls the world. And I really don't like quoting Vladimir Putin here, but I think it's it's still a bit of a stretch, but it's essentially true. And actors like Vladimir Putin, actors like the President Xi in China, these actors will not really care too much about consumer rights. It's a good thing that we care about consumer rights, but what will be the rights of consumers in our countries when we let other non-democratic actors to control AI? Then the shift of the part of AI development to illegality, which might be of a paradoxical consequence, because we want to make AI more transparent, but as a result we might end up making it less transparent, because it will be just, of course, for example, large language models are extremely expensive to develop, but still, if a part of this development shifts to illegality, it might be a problem. And then the other problem might be, which might not be so obvious at first glance, but if we adopt too complex or too detailed regulation, it might actually strengthen the monopolization of AI development. And just notice that the biggest companies literally call for AI regulation. Are they doing this because of their good intentions? Maybe partly yes. I'd also be doing that because they know that they can invest in compliance. They can invest a lot of money in these compliance programs. But the smaller startups, smaller developers might not be able to do that. And quite paradoxically, we may end up hindering this free competition in AI development by doing that. And there is, I don't know whether it's consensus, but a lot of people say, and I can agree with that, that what perhaps would be the safest option for a new AI ecosystem is a multi-AI ecosystem, multi-modal ecosystem in the meaning of many AI models that compete, that tend to be, the smaller systems usually are more prone to be open source than the biggest systems. And this might really be the safest option. So we shouldn't really go against this trend. And there are also some partial problems. For example, some specialized models that might not be as big as those large language models are now better for the use in medicine. And of course, there is again this problem that startups might not be really able to comply with a too detailed regulation or too strict regulation. So traditionally, in some legal systems, the problem with what we might call now entropy was solved by focusing on individual problems. This is more of an Anglo-American law thing. The continental law was always, or has always been, more about abstract ideas and about finding solutions that are applicable to the society as a whole. But still, I believe that this might actually prevent us from focusing on the single cases that might then be generalized. And this is one of the ways that can lead to actually decrease in entropy in the system. So the question is, should we rather focus on applying the already existing legal principles and rules first, and then try to come up with the best possible special regulation only when we find out in practice that these already existing principles don't work? Just take a bit of an example. It's more about discussion than actual regulation. But some year ago, there was a lot of discussion on biosecurity, and people were saying, okay, large language models will lead to almost everyone being able to develop some new biological or chemical weapons. And today, the mainstream discussion has shifted a lot, because it might not be that people overestimated the ability of large language models to help you develop some biological weapon, but the problem might be that many people underestimated the availability of the information that we have now. So it's if someone has the resources and wants to develop some biological weapon, it might not make such a big difference whether they are LLMs or not. So today we focus more on clarifying and strengthening existing regulation, existing policies, than trying to come up with something entirely new. Still, the problem is that we really need to protect the rights of persons. We really need to protect society. We need to promote trust. And I do believe that when we are talking about healthcare, trust in the doctor-patient relationship is a cornerstone of healthcare for many reasons. And we have seen it in the COVID pandemic, for example, what can be the consequence of the loss of trust. So I'm not saying that we shouldn't regulate AI. I'm just saying we should do it in a reasonable way. And perhaps if we focus on legal liability for the breach of these existing principles, if we really try to strengthen and enforce the existing rules, existing principles, on the way we will face many obstacles, and on the way we will need to solve them. And we can solve many of these obstacles by case law. We can solve many of these obstacles by thinking through these problems and applying the existing regulation without the need to come up with some super detailed new rules and new legal norms. And in this way, the public can experience the sense of control. Many people are scared of AI because they are scared of losing control. Not only losing jobs, but losing control on the world we are living in. So the public can experience certain sense of control because the regulation will be understandable and it will be sufficiently stable over time. If we come up with a new detailed regulation, we are probably going to need to change it a lot. And this will contribute to the atmosphere in the society that things are getting out of hand. So perhaps it's a wiser solution to use these already existing problems. And for example, there was no new book in civil code. I'm sorry for my Brazilian colleagues. There was no new book in the civil code, the whole industrial revolution. And many legal institutes we are using now are the institutes that were invented in the old Roman Empire or even before that. And we just had to learn to apply them today. And this civil liability thing, this is more of an example, because there's a lot of talk about new civil liability regimes for AI in medicine. I don't think we need them at this point. Sometimes some authors even say that we should introduce a new legal person, something like an electronic person. Well, once we achieve AGI, we might talk about it, maybe, but it's not the time yet. If the AI model is a medical device, then we have a special, these are examples of Czech law, but I believe it's similar in most legal systems. We have a special liability for defective thing. So this is fully applicable. If the harm is caused by the black box nature of AI, then we still have a liability for damage caused by a thing itself, caused by a thing that was not defective, because we cannot really say that a black box is a defect. It's the nature of AI models. But still we can use a liability regime that we already have at hand. And in principle, existing regimes of civil liability, in my opinion, sufficiently cover all those possible scenarios where harm might occur. And of course, we will face problems. We will need to think hard about how to apply these regimes, but we don't necessarily need to introduce some new regimes or to change them fundamentally. So, as a conclusion, what I wanted to say today, we can expect a wave of specific AI regulations. It's bound to happen now. But too complex regulation has several dangers. It might increase entropy in the legal system, make it even more chaotic than it is now, and you know that most people are not really content how chaotic their legal systems are. It might even monopolize AI development with all the problems that will come with that, make it less transparent, paradoxically, and strengthen the geopolitical position of those actors that will not really care about ethical and social and legal consequences of AI deployment. So this solution that I would like to propose, or I would like you to think about, is that we should rather focus on interpretation, application, strengthening, enforcing the existing rules, and enact new specific rules only when we see, only when we experience in practice that those existing rules cannot be applied sufficiently. And as an appendix, all those existing liability regimes, in my opinion, are quite sufficient to cover the harms, even harms in medicine that can be caused by the use of AI systems. So, thank you very much for your attention.
Do we have questions? So the last question again.
Thank you.
So, no, this was great. Liability is an important one, right?
Yeah.
And you say existing liability can work. Okay, let's take an example. I'd love to take one in AI in medicine because
sure.
The question is, I won't, because there is an interesting question of should the software developer be held liable? Because I don't think the black box by itself, that's not an excuse. There is some computer scientists who built the algorithm. If the algorithm fails and somebody dies, who is at fault?
Yeah.
But the actual question I want you to answer is self-driving cars. Okay? Who gets the ticket? Because if I drive a car, if I run a red light, if I run whatever country you're in, if you run 4 red lights or 5 red lights, I will lose my license. Okay?
Yeah.
So what happens with self-driving or semi-self-driving cars? Who should get the ticket?
Thank you. I think that the answer might be easier in the semi-self-driving cars, because if I am still sitting behind the wheel, even though I don't need to be touching it all the time, then I believe I can be held liable for what the car does. And the full self-driving cars, it's a more complex question, of course, but I still believe that we will need to have this discussion, but I still believe we can solve it under existing regimes. For example, I think in the Czech point of view, or in the Czech style of thinking about these matters, I would still think that the owner of the car should be held liable for that, because it's his car, it's his liability. And if this car is getting a rogue, then it's a fault of this product. And then we can also think of the product liability of the manufacturer of the product, or of the person that introduced the product on the market. So still we can think, the point is that still we can discuss about these things and about these matters, and we can find a solution in existing regimes.
So I just want to be specific. Okay, yeah. In the US we have self-driving taxis now.
Yeah.
Right? So I've just written one. It's actually quite fascinating.
Yeah.
But in case of an accident, right now we have, it's owned by a big company, right? It's not one car owned by one person. I can get there. But a fleet of cars, 10,000 cars owned by Google.
Yeah.
If one of those cars gets into an accident, who is liable?
Well, from the point of criminal liability, no one should be liable, perhaps, unless it was some fundamental flaw.
The road was wet. The road was icy.
And if the road was icy, and it was not a fundamental problem, it was something that a human driver could have done. Because a lot of times there's for example, sometimes there's an accident, or there have been accidents with self-driving cars, and everyone was like super excited that there was an accident in self-driving car, even if it was in a situation when a human driver would quite likely make the same mistake. So in these cases, I would say, okay, there would probably no criminal liability, but from the civil liability point of view, the compensation for harm, the owner should be liable. For example, if it's similar, like if I'm in a Czech system, at least there's there is strict liability for harm caused by a vehicle in traffic. So if this vehicle makes or creates some dangerous situation ending up in a harm, then the owner of the vehicle or the one who runs this traffic is liable for that. So I think it might be the same. Okay, thank you very much for that. And I think in the case of these medical AI systems, it could still be similar. Sometimes it's the manufacturer, sometimes it's the provider of health services, the owner or the deployer of the AI system, and we can still think in line with these old regimes. Okay, thank you.
Or it will be actually answered by the first big legal case in the court.
Yeah, it will be super interesting.
For you. Okay, thank you once more.
Thank you very much.
So next we are having Eugen Hruška, right? Yes. This is a nice cross-section of the faculties of Charles University. So Eugen Hruška is from faculty of pharmacy. He has a nice history of education. He studied at Ilmenau, Regensburg, and then finally got his PhD at Rice University. Correct?
Yes.
Correct. And he will tell us about AI in pharmaceutical science. Please.
Thank you. So there are many phrases which you heard now and probably a lot with AI, like some convolutional neural network or specificity, or there are just many phrases. And today you heard about rotation in equivariant convolutional neural networks, my favorite up to now. So there are many phrases, and I assume many in the audience here know some or all of them. But the general audience might not know all of them or understand what they mean. And if someone explains that this self-driving car made an accident because specificity is something, does that help the general audience or not? So this is the general situation. I'm at the Faculty of Pharmacy, and I'm interested that the students which develop some science for pharmacy understand what they are doing and not just having black box happening. So what I did is create a course to explain that, because some students are actually very interested. They might understand most of these things, but not all of them. So this course was a doctoral course and not the undergraduate yet. Plans for that. So it's purpose-built for pharmaceutical science, because the doctoral students develop and write papers for future pharmaceutical science, including the AI part. And there are some domain-specific aspects which are not the same in self-driving cars, something. For example, there is limited public data in many endpoints relevant for pharmacy. And there are some even rare diseases where you have only 100 patients. There are like very extremely limited data on that. And there are many, many different diseases. So previously we heard that different aspects of predictions might have different conclusions. So you might be able to predict one thing well, but something similar sounding might not be able to predict well for different reasons. So these endpoints are very specific. And if you want to develop them, you have to understand how to pick these endpoints and why. And of course, then explainability. Explainability, it turns out, has different meanings. There's explainability from the computer science perspective, like which bit or vector in this AI explains what. But you have also the science explainability in the terms of language of science, what causes what, and so on. And in the pharmacy, we have regulation that you actually, your pill or whatever that is, actually does what it's supposed to do. So all these aspects, I create a course. So I will focus on like syllabus and learning outcomes and so on. I started with the learning outcomes. I wanted to, was thinking, what should the student know at the end of the course, which they do not know at the beginning? So there are practical and theoretical aspects. So practical, these students should be able to train and deploy some of the models which were discussed previously, like these small random forest or something like that models. At the university, we do not have resources to train an LLM at this point, but the students, this is a beginner course, should be able to do that. So basically from 0 to like a small machine learning model. And there are aspects to that. So we have like, you get some data, analyze this, load it to the computer, and just some very standard machine learning software, and be able to create and deploy this model. So this was my purpose, that they should be able to do that. It's quite standardized at this moment. So at the side, I've shown you here what kind of the Bloom's taxonomy, what kind of type of learning outcome it is. So we have this knowledge, comprehension, application, analysis, synthesis, and evaluation. So this part is mostly application. So you do something, the student should do that, and comprehend what kind of data and what to use around it, and analyze the results. So this is like this middle level of AI. When you do a paper, that's probably the meat what the doctoral students will do. Then I continued with theory. So with application, we also need a shared background, what the student should know. So this is specific to pharmaceutical science. So if you do the same course in mathematics or something, might be different goals. So I started with general machine learning. So we have questions like, how do you data split? So there was validation and training data, cross-validation and so on. The students should know these basic stuff, but also to explain why this machine learning just not memorize things. It's not literally memorizing a list of data. It has some kind of extrapolative properties. Why does it do that? And how does it solve problems like overparameterization and so on? So like this kind of general understanding. And then some general structures, which we even heard today, like convolutional neural network, a random forest. Like being able to describe it, this is a pharmacy faculty, so we do not generally develop new architectures. So that's the computer science. But we apply them, and we have to know when to use which one. So like this kind of not purely theoretical understanding, but like more applied understanding what's doing and why and when it's not working as intended. So, and then basic like back propagation, gradient descent, and also some aspect of explainable. Turns out every year it's like developing this field. So I had to like update my course while creating it. And here in the Bloom's taxonomy, it's all knowledge. So this learning outcome, since I shared with the students, they can just memorize that, but I think it's still useful. Like these are kind of general questions, at least when you like apply small models, you should be able to answer these things. So memorization for the students is still useful in this sense. And then that was general. Then I looked at specific to pharmaceutical science. So we work a lot with molecules, small ones or large ones, antibodies, proteins. So we have to represent them. For molecules, there's a list, an expanding list of representations for these molecules, and the same for proteins, and they are not trivial. So for example, there was mentioned the rotation equivariance. That's one thing which is important in a pharmacy, because you rotate your protein, it's still the same protein. Like you might know in AlphaFold, one of the like breakthroughs in protein folding structure prediction, there is equivariance layers. So in the course, when I was explaining how this AlphaFold working, it's not a black box. You can look in the code how it infers the prediction and see this is equivariance layer. Of course, for that, you need quite a lot of mathematics. So there's this trade-off between accuracy, how deep we want to go in each question. So that's why picking the learning outcomes is very important, because there are so many questions, and these students might be interested in some of them, but other questions might be relevant for them. So picking the learning outcomes in the course is very important. So that's why I'm discussing that here. We have some specific structures, architectures like graph neural networks, which are more popular in these kind of molecular representations or transformers. So we have to describe that. So of course the equivariance, understanding what it is, but also when to use them, when not to use them, since that might be relevant. Molecules are not the only thing we work with. We have also reaction condition for the synthesis. We have to create molecules. We have also like data gathering. AI can be used for that as well. So many different fields of AI to kind of understand. So with these learning outcomes, I started building this course. I picked the topics mostly from the theory. So I started with the general course, like you might find in the computer science, what data splitting, loss function, supervised, unsupervised one, classified, and so on, even some practice ones. But I realized just copying the whole course from computer science will not go very far in pharmaceutical science, because going very deep in mathematics in pharmaceutical science might not be relevant. We do not want to, like most of the students do not want to develop a new architecture. We want to apply architectures. So I focused on how to apply existing architectures. There is already software for that, how to retrain, how to fine-tune, how to infer, how to deploy these models. And of course, hyperparameter tuning, some optimization. In pharmaceutical science, multi-objective optimization is important because we do not only want something which is heals your disease. We want also something which is safe, it's stable, it's not toxic for human or others. So all these endpoints, there are like dozens and dozens clinical endpoints which are relevant, and all of them have to be achieved. So previously we talked about regulation. There is a huge body of regulation already there. So it's clear that we have to meet all these points. And as was discussed previously, these points might be fine-tuned when considering the impact of AI on pharmaceutical science. But they are not, these questions are not new. So we know what kind of endpoints we have to fine-tune, but there are just many, many. So multi-objective optimization is also part of it. Some uncertain estimation and explainable predictions, why that is not only correlation, but also causation. And then generative models. Generative models is interesting because we have the generative models for text, but in pharmaceutical science, you could consider we want to generate molecules. There's a huge space, 10 to the 30 of something molecules conceivable as drug compounds, and we want to pick the one which does what we want. So the 10 to the 30, it's not enumerated, but there's a huge list of molecules we already try. So there are groups which want to generate like which of the molecules just to try. Turns out my colleagues kind of ignore that approach, mostly, because that's not their problem. Their problem is we have a huge list of molecules and how to pick the ones which meet all these endpoints. Safe, heals this disease, and so on. So we have literally billions of molecules you can order online. Generating more billions of molecules is not really solving their problem. So there are a bunch of papers on that, of course, and companies trying to work on that, but that's not their priority problem, I would say. The problem most of my colleagues have is how to pick or adjust slightly the molecule to meet all these endpoints. There's also diffusion models. So these architectures are evolving. So every year there's something new happening here. Here I'm put also model deployment. Model deployment in the previously was somewhat difficult, and it was left to the software people, to the computer scientists. But I think at some point, the pharmaceutical scientist, when you don't create something, you might not trust this. So it's like a black box problem. So the more of these steps, everything from start to end, will be in the hands of someone who's also then like responsible for like these regulations by EMA or FDA, the more this will be trusted and can be iterated on. So it was mentioned previously that the timelines of pharmacy and computer science are very different. We have these 3 months or something timelines for publishing on a conference for computer science, pharmacy 10 years. So to align that, it's almost like a culture clash. So transferring this information, you have to pick which information to transfer. And so you don't get cultural misunderstanding. So that's why there's all these learning outcomes. So here I highlighted some of these challenges. So if you want to not only like be an end user, which uses this tool and maybe do prompt engineering, but also like develops it and creates for specific data sets, for specific use cases, then you have to understand the concepts, and that involves math to some level. So like the loss function, classification, specificity, and so on, multi-objective and optimization, all maths. So I did not put any prerequisite for this course. I put like a soft one because everyone was invited and aspects of the course would help anyone, even without any maths knowledge. But there were aspects where the students realized and they asked a lot of questions and they kind of got stuck. And I had a dilemma. Do I teach the students mathematics to cover this, or do we skip and they will have gap in the knowledge for these learning outcomes? So this is kind of a dilemma I encountered, and I believe we will just need to improve the mathematics fundamentals for these kind of courses if we want to develop models. If you just want to do prompt engineering, that's not really necessary. Also, a soft prerequisite is coding. So these software stacks, it's mostly in Python or R or something like that. And it's not like very difficult coding, but still, in these practical aspects of the course, the students, which already had some experience, but not much, they kind of got stuck. So, and I saw a huge drop in participation in the first course, where there was motivation and so on. Everyone was interested, great. And then in the second course, where there's a bunch of math and some coding, I assume it's basic, but you have to like break it down and get everyone on board. So this is a software prerequisite because I saw students which start with almost no coding experience and get successful on that. So, of course, we have to think about what kind of practical the tutorials and exercises we do. So I picked the software stack, everything in Python, everything in Jupyter Lab. So it's more, I would say, user-friendly something. There is a combination of images right next to the code, so easier to connect what's doing what. It's not as easy to debug, but it's fine. So I picked like the standard tools, Pandas, sklearn, PyTorch. So to cover the very generic ones, but if you want to do pharmaceutical specifics application, there are specific packages like chemprop, depurpose, where someone already published that, and you can just pick a different molecule and different disease and just change the data and retrain it and get to not state of the art, but close to the state of the art within a couple of hours. So I went through these packages, which obviously are changing every year because the state of our art is changing. But I found it very useful for the students to show them that how these basic packages, which are not pharmacy specific, apply to pharmacy specific questions. So when I was developing this course, there are many open source courses you can see on machine learning or AI or something like that, and like classify cats and dogs. I removed all these examples because all the students in the pharmacy faculty obviously are interested in pharmacy. So I put examples relevant to them, no cats and dogs there. There's also some more complex representation, convolutional neural network, of course, for the X-rays, rotational equivariant ones, which are possibly more difficult. We have also transformers. When you have retrosynthesis predictions, there's these transformers models, which are essentially large language models just trained on these customer reactions. So again, retrained or AlphaFold, which is for the protein fold prediction. The problem with these, some of them they're not very user-friendly to retrain within 30 minutes. So you have to scale it down and pick the simplest one. So for example, AlphaFold, you cannot even retrain it. Only the inference code is available, and for AlphaFold 3, not even that. So it's getting more and more black box. So instead I used OpenFold, which has open, you can train it, you can make it smaller, something like that. So everything simplified the tutorials for me. So the transformer is also for the generative models. And so explaining the transformer, every part, how it works, is quite difficult. So I kind of stayed on the level of what is attention, what is the layers, and essentially giving the students all the tools to be able to go further if they have not heard about that. We have to also cover science and regulation, causality, and explainability. This was one of the challenges which I encountered when developing this course, because there are many open source courses, even more specific to chemistry, for example. Some similarity there, but they might they might have different strengths. So I picked and chose from these open source tutorials, which I will copy and do something similar on, and teach the students these aspects depending on the learning outcomes I started with. So at the end, the course looked like this. So I separated in passive and active. Active, or where the students actually do something actively. So these are the soft coding aspects, data splitting, training, some basic ML, hyperparameter tuning, some PyTorch, and some walkthroughs. So I hope to get further to retrain some specific pharmaceutical models which are state of the art, but at the end of the semester we run out of time. So there's still room to improve to get this longer and further develop that. As far as passive, all these motivations and examples of failure cases where the CNN kind of didn't look at the actual X-ray, but like the labels on the side of the X-ray. Like all these, like to warn essentially so the students do not make the same mistakes as was done in the past. So this was like the introductory lesson, and the second one was more mathematics, gradient descent, all these types, but not very deep, more to be applied. I invited some external lecturer which does current research in this field, so the students have understanding what the current state of the art in this domain is, And so they also they were able to meet and discuss with that researcher. So I think at the doctoral level that's is useful. In undergraduate, I'm not sure if it's feasible, but worked well. Here, then I continue with hyperparameter tuning, so essentially building on the previous coding, like doing stepwise. So we cannot just jump in the deep end of the machine learning creation and deployment. We have to do step by step. So here we have hyperparameter tuning, deploying, and getting more difficult representations, and some more explainability and more applications. So you see two parts of application at the beginning, at the end, hopefully in the intermediate, when the students understand all these details, they appreciate the applications better. With that, I want to share some takeaways I encountered. So I did not open source this course yet. It's not at the level, but I'm planning to do that. There is a difference between quantitative and qualitative AI, machine learning. Depending on your use case, might be different. In pharmaceutical science, we need to be like precise, have randomized mice controlled trials, so be precise that. In pharmaceutical science, low data is a very common use case. In protein folding, there's larger data, and LLM are quite, it's one application in pharmaceutical science, but it's not most of them. If you look at the state of the art, only in some areas. We have some limitations on mathematics, on coding, if you want to actually deploy at the doctoral level. There's many other courses which have strengths and weaknesses, and just pick the ones which are most useful. At the end, students asked me to share tutorials, links, and so on, what I created everything with. And all of this open. So if you have internet, you will find everything of that. But turns out, having the experience to figure out which of these tutorials, courses is the best one is a huge question. So sharing what I consider as an expert in this area, the most relevant for like at the beginning or even advanced ones was very useful for the students. So there are even whole tutorial series which are useful. So I feel there's this, as AI is developing, each domain will create like their own courses which are fine-tuned to this area, which is relevant. Not everything is relevant to every domain. So here I shared my lessons and takeaways. Hopefully it will be helpful for other people developing courses. Thank you.
We are slightly running behind time, so the last question immediately.
Thank you. So I would highly encourage this for undergraduates as well. I mean,
yes.
I would actually argue that every undergraduate student needs to take this course or a course like it, because it's fundamental learning of how to live in society.
I agree. The reason I started with doctoral is organizational. Like there's a higher requirements to get the undergraduate course approved than a doctoral course. So this was like the test case. Now that I see what worked, what did not work, I just transform into the undergraduate.
Thank you again. So we've got Martin Richter now from the Faculty of Social Sciences. This talk will be in Czech, and it's he's from Center for Strategic Communication, and it will be about curiosity and concerns.
Yes.
Please, Martin.
Yes, thank you for introduction. Yesterday evening, when I tried to upload my presentation to ChatGPT and provided website of this conference to get feedback on my work, it told me, well, that looks like fierce competition, and gave me 8 recommendations to change my work. So for something what supposed to be supportive, it really scared me. So apologize. I'm going to continue in Czech. Já bych se chtěl dneska věnovat tomu, kdy se bavíme o umělé inteligenci i v kontextu duše a našeho vnitřního prožívání, tak bych se chtěl podívat na emoce a prožívání emocí v kontextu toho, jak na nás umělá inteligence působí. Já rozhodně nechci působit jako výzkumník, nejsem výzkumník, jsem student doktorského studia, kde zároveň můžu působit jako vyučující předmětu umělá inteligence v komunikaci a zároveň jsem spoluzakladatel a lektor v neziskové organizaci IGNOS, která se věnuje vzdělávání o umělé inteligenci. Díky tomu já mám možnost setkávat se s velkou spoustou lidí. Jedna skupina může vypadat takhle, vypadá jako vy, jsou to dospělí lidé, a ta druhá skupina vypadá nějak takhle. A musím říct, že tahle mě hodně baví. Tenhle segment mladých lidí je opravdu studnice zajímavých poznatků, se kterými já se musím nějak vnitřně vyrovnávat. Jsou to Zetka, takzvaný generace Z, jsou to digital natives, je to TikTok generace, je to kohorta mladých lidí, která vyrůstá s umělou inteligencí. S největší pravděpodobností to bude generace, která bude obrovským způsobem ovlivněna touto technologií. Jak v denních činnostech, tak ve vzdělávání, ve škole, ale i v kontextu jejich budoucího zaměstnání. Tohle bych chtěl doplnit možná takovým konkrétním příkladem, jakým způsobem se teďka mění svět, náš každodenní svět. My jsme si vlastně nedávno zvykli, že existují influenceři, setkáváme se s nimi, dokážeme je poslouchat, dokážeme se jimi nechat ovlivnit. No a teďka přichází nový fenomén, který se nazývá AI influenceři. Jsou to AI generované osobnosti, které zasahují do našich životů, zřejmě ne našich, ale třeba tady Lil Michaela je AI influencerka, která má skoro 3 miliony followerů, což je vlastně docela zajímavý sociální experiment, jak my jako lidstvo budeme reagovat na entity, které nejsou lidmi, ale zasahují do našich životů. Můžeme se s tím vyrovnávat třeba pomocí AI kouče, který nám se s tím pomůže vypořádat, takže jsme se had se zakousl sám do sebe, zacyklilo se to a obavy, které způsobuje umělá inteligence, bude zároveň umělá inteligence s námi řešit. To ale se snažíme nějakým způsobem reflektovat v tom, jakým způsobem vzděláváme mladé lidi. Snažíme se předávat základní principy toho, jak se s umělou inteligencí pracuje, na jakých principech funguje a jaký má samozřejmě současné možnosti využití. Ať už to jsou AI influenceři, anebo klasičtí chatboti, se kterými my si povídáme docela často. Samozřejmě ale se zabýváme i limitacemi a případnými riziky, které tato technologie nám přináší. A určitě bych zmínil problémy biasů, zkreslení, dezinformací, generovaných dezinformací, nebo dopadům na naší pracovní uplatnitelnost a well-being. Zároveň se snažíme v každém workshopu nebo v každém semináři, který děláme, nezaměřovat se pouze na tyto technické parametry, dejme tomu, ale i na to, jak tuto technologii nevyužívat pasivně, ale aktivně k tomu, abychom se sami rozvíjeli. Aby když už jsme konzumenty AI generovaného obsahu a spolutvůrci generovaného obsahu, tak abychom tento generovaný obsah využívali k tomu, abychom sami sebe rozvíjeli a zároveň ale ty výsledky, který nám to přináší, abychom podrobili kritické diskuzi. Jak ale tuhle situaci vůbec se snaží, nebo jak ji vidí generace Z a mladí lidé, to je docela trošku složitý, protože já osobně to úplně nevím. Já mám spoustu domněnek, spoustu zkušeností, ale nejsou podpořený daty, protože spousta nebo většina výzkumu, který probíhá, je zaměřen na dospělou populaci. A nebo když už máme nějaké výsledky na mladou generaci a jejich vnímání umělé inteligence, tak je většinou ze zahraničí, což v našem sociokulturním kontextu nemusí být úplně relevantní. Proto jsme se snažili analyzovat naše data, které jsme získali vlastně takovým docela přelomovým a zásadním období, a to je vlastně od ledna roku 2023 do května 2023. Byl to takový první hype chatu GPT, ono jich asi bude postupně přibývat, jak se budou zveřejňovat další modely. Vlastně nedávno zveřejněný model 4o toho může být takovým důkazem. A vlastně máme docela robustní skupinu respondentů, bylo to přes 1000 studentů z koutu České republiky a samozřejmě jsme k tomu využívali anonymizované dotazníky. Ty hlavní statistiky, které jsme z toho jsou pro mě ne až tak překvapující v téhle perspektivě, ale když jsem je viděl před 3/4 rokem, tak mě vlastně docela zarazili, protože už v tu chvíli, kdy byl ChatGPT zveřejněný pár měsíců, tak už vlastně přes 60% studujících mladých lidí, i školáků na základních školách, vnímalo umělou inteligenci jako něco, co jim bude zasahovat do jejich pracovního života, a vlastně pro 85% skoro mladých lidí téma umělé inteligence vlastně působilo jako velice důležitá věc, který bychom se měli ve společnosti věnovat. Snažili jsme se i o to, abychom vám předali grafy, které nemají data. Za což se omlouvám a nevím, jak se to stalo, ale já se teda zapnu svůj jazykový model a budu se snažit interpretovat to, co na těch grafech je, aniž by tam ty čísla byly. Tak já vám pak asi poskytnu tu prezentaci v PDF, kde mi nevypadne font. Snažili jsme se zjistit, jakým způsobem mladí lidé jsou sebevědomí v tom, kolik znalostí o umělé inteligenci mají. Snažili jsme se, ty dva grafy ukazují to, jakým způsobem hodnotili svoje sebevědomí před našimi workshopy a po našich workshopech. Ta tmavší barva znamená nebo ukazuje, označuje procento těch, kteří svoje sebevědomí hodnotili jako podprůměrné, ta světlejší to byli ti, kteří své sebevědomí hodnotili jako nadprůměrné. Je vidět, že před workshopem drtivá většina respondentů své sebevědomí hodnotila podprůměrně. My jsme velice rádi, že po našem workshopu se to sebevědomí zvedalo. Jestli je to správně nebo špatně, to já úplně nechci hodnotit, ale vidíme, že tam nějaký posun probíhá.
Ten průměr byl průměr té skupiny, anebo průměr obecné generace?
Průměr té skupiny. My jsme se snažili také získat data o tom, jakým způsobem vnímají mladí lidé emoce v kontextu umělé inteligence. Měli jsme tam zvídavost, obavy a úžas nad tou technologií. Teďka vám to úplně nedokážu z hlavy interpretovat, ale je vidět, že vlastně po našich workshopech se zase pociťování emocí, jako je úžas a zvídavost, zvyšuje, přičemž hrozby nebo pociťování nějakých hrozeb a obav v kontextu umělé inteligence tak se mírně snížily, ale tomu bych nedával až takovou váhu. Snažili jsme se i ty data nějakým způsobem provázat, jestli spolu nějak korelují. Zjistili jsme, že jsou tam slabé pozitivní korelace, které jsou ale statisticky významné, takže tím, jakým způsobem roste naše sebevědomí v tom, jaké znalosti o umělé inteligenci máme, tím roste i naše zvídavost, i vlastně úžas, který pociťujeme z této technologie. Zároveň se ale nepotvrdilo to, že s rostoucím sebevědomím klesá náš pocit obavy nebo negativních dopadů na nás, což mě vlastně docela překvapilo. A tam se nepotvrdilo, že by to mělo nějaký statisticky signifikantní podíl. Zároveň jsme se i zaměřili na to, jestli vlastně to sebevědomí nějakým způsobem je spojené s tím, jak vnímáme umělou inteligenci a její důležitost v kontextu, v obecném kontextu, anebo i v kontextu vlastně dopadů na naše budoucí pracovní uplatnění. Tam se ukazuje, že ty pozitivní korelace tam jsou. A vlastně čím větší sebevědomí o tom, kolik toho o umělé inteligenci víme, tak se může projevovat tím, že si myslíme, že nám bude zasahovat do našich životů víc a víc. Z toho bychom chtěli vyvodit několik závěrů, a to, že i přesto, že jsme se vlastně věnovali v těch workshopech vlastně docela závažným tématům, které zahrnovaly vlastně docela podstatné hrozby a případná rizika, která tahle technologie přináší, i ve velice praktických ukázkách, tak vlastně tenhle způsob toho, jak jsme studenty a mladé lidi vystavili těmto rizikům, tak to nesnižuje jejich zvídavost a jejich chuť se něco dozvědět. Zároveň bych chtěl zmínit další konkrétní doporučení pro to, když se budete věnovat vzdělávání o umělé inteligenci, na jaký konkrétní body se můžete zaměřit a který nám můžou pomoct v tom, abychom byli odpovědnějšími vzdělávateli tady, co se týče konkrétně generativní umělé inteligence. Z našich zkušeností vyplývá, že je dobré se zaměřit na praktické projekty, které pomůžou podpořit a zvýšit kreativitu, tvořivost a představivost u mladých lidí. Máme s tím velké zkušenosti. Měli jsme několik výstav, které to potvrdili, že mladí lidé, pokud vědí, jak generativní AI ovládat, tak jsou velice schopní a velice kreativní a vytvářejí velice zajímavá díla. Zároveň bychom se měli zaměřovat i na well-being a na to, jakým způsobem nás technologie umělé inteligence může tady v tom pohledu ovlivňovat, protože ten dynamický vývoj je stále rychlejší a těch změn začíná přibývat. Zároveň bychom chtěli, nebo ve všech workshopech my to děláme a snažíme se v tom pokračovat dál a ve větší míře podporovat a motivovat studenty k tomu, aby AI využívali nejenom k tomu, aby si usnadnili práci a aby rychleji odevzdali seminární práci, domácí úkol, anebo napsali e-mail, ale k tomu, aby rozvíjeli sami sebe, aby tu technologii nevyužívali jenom jako nástroj na zrychlení nějaký pracovní workflow, která je nebaví, ale k tomu, aby se snažili něco nového naučit. A já jsem si pro vás připravil i jednu takovou praktickou ukázku. Můžete vyzvat našeho debatýra, kterýho můžete naskenovat tady na QR kódu. Je to vlastně taková simulace přes ChatGPT personu, takže pokud máte placenou verzi, můžete si vyzvat na souboj našeho debatýra, který je napromptovaný k tomu, aby byl záludným konverzačním partnerem, aby rozhodně nebyl milý, nedával vám nic zadarmo, aby vycházel z eristrické dialektiky od Artura Schopenhauera, využíval všechny záludy v tom, jak vás přesvědčit, a využíval třeba metodu úhybných manévrů, kterou známe z politiky. Takže můžete si to vyzkoušet a zároveň, pokud toho debatýra požádáte, tak on vám dá zpětnou, docela komplexní a takovou konstruktivní zpětnou vazbu, jakým způsobem dobře komunikujete, co byste mohli zlepšit a jakým způsobem být lepším debatýrem, abyste měli takový skillset, abyste přemluvili i někdy nepřemluvitelnou umělou inteligenci. Já vám děkuji za pozornost, to je ode mě všechno.
Otázky? Questions?
Děkuju. Já bych měl 2 otázky. První je, jestli jste pozorovali nějaký rozdíly mezi muži a ženami.
V kontextu toho, že jsme chtěli být co nejvíc anonymizovaní v těch dotaznících, které šly vlastně na lidi, kterým ještě nebylo 18, tak jsme se snažili vyhnout co nejvíce možným údajům, který by to mohli v kontextu nějakého GDPR vlastně tohle stěžovat. Takže jsme nerozlišovali mezi dívkami, chlapci a ostatními.
Chápu. A ta druhá, ten kontext toho wellbeingu, já se přiznám, že tomu moc nerozumím. Oni mají nějaké obavy jako z budoucího trhu práce nebo z těch technologií samotných, nebo můžete to prosím nějak rozvést? Mm-hmm.
Jo, my jsme tady v tom dotazníku, který jsme vlastně sbírali, tak se přiznám, že těch obav jsme mohli zmínit víc, což jsme neudělali. Takže nemáme úplně konkrétní data o tom, čeho konkrétně by se obávali. Z hlediska i toho, že to jsou prostě mladí lidi a jejich attention span je asi tak jako 2 minuty, takže jsme museli být co nejkonstruktivnější a zjistit aspoň pocit obecných obav z té technologie. Ale když budu mluvit ze své zkušenosti, tak tam vznikají obavy právě o pracovní uplatnění. Spousta žáků i mladých lidí, i vlastně i v kontextu vysokých škol, tak se ptá, studuju vůbec tu školu, jsem tady správně? Má to smysl? Neměl bych dělat úplně něco jiného? Bude moje zaměstnání ještě za rok, za 2, za 5 existovat? A to nejsou jediné hrozby, ale jsou to hrozby i o vlastní soukromí, o bezpečí svých dat, anebo nějaký diskriminace, co se týká biasů, který konkrétně v jazykových modelech jsou a můžou nás třeba ovlivňovat ve věcech, jako je třeba, jestli dostaneme hypotéku, anebo pokud by to využil nějaký učitel třeba na nějakou evaluaci jejich výsledků, tak tam můžou být třeba nějaký rizika. To jsou jako takové základní věci, které já si teďka ze své zkušenosti vybavím, ale ta moje dlouhá odpověď směřuje k tomu, že nemáme konkrétní data.
Děkujem. And the last speaker is Michaela Ligertová from Ústí nad Labem. She got her master degree there, but PhD at the Faculty of Science at Charles University, and after some time working in the Academy of Sciences, she is now back in Ústí nad Labem, and she works in AI in education and research conduct. So we will hear something about that.
Thank you for the introduction and thank you for the invitation. And my talk will be focused on how generative AI could be integrated into helping professions, education, and how it can be leveraged to create dynamic learning environments and simulate interactions with patients and clients. And to save time, I will provide only a minimal definition of generative AI as a set of algorithms which analyze users' input to create original, relevant, and context-specific outputs. And there are many advantages of generative AI. For example, it's the enhanced simulation capabilities, personalized learning, which could be tailored to individual student needs, innovative educational models, but what is even more important, it prepares students for the AI-driven professional environments they are going to face soon. Of course, there are many drawbacks and risks. the algorithms may replicate biases from the training data and produce factually incorrect information that can affect the educational content quality. There are ethical and privacy concerns, but also the over-reliance on AI could undermine the critical thinking and decision-making skills, as well as could lead to depersonalization in the essential human interaction. I'm focused in this talk on applications that do not require coding. And my goal here is to inspire the educators here in the audience to go and experiment with the tools and to try to use them and create or generate some learning aids for their educational context. And I will be mainly talking about the large language model-based chatbots and cover uses from simple prompting to custom instructions over custom GPTs and customized chatbots to multimodal agents. I will also touch a little bit of more complex workflow where you combine various generative AI tools together and also mention some of the most recent experimental tools. Large language models-based chatbots could be very good for generating various cases or scenarios for case-based or problem-based learning contexts, and this could lead to developing problem-solving and critical thinking skills for the students. You can create diverse case libraries, you can translate them into multiple languages, you can adapt them culturally to prepare the students for diverse patient populations they could meet during their work. On the other hand, you can use the chatbots to create interactive simulations or role-play scenarios or multi-perspective engagement scenarios, use it for crisis intervention training, ethical dilemmas training, and so on. Okay, I think maybe...
Last slide.
No, it's not last slide. It's probably this thing is not working. Oh, it just moved. Okay, perfect. Thank you. I'm going to talk about ChatGPT-4 as an example, because you might know that the GPT-4 version is becoming freely available for everyone to use, which makes it, according to my opinion, one of the best options you can use as educators to create learning materials for your students. And using ChatGPT, you can generate learning aids by simple prompting, as I mentioned already, to generate some cases or scenarios. You can use custom instructions to create more complex virtual patients or client simulation to practice direct interaction, interviewing or diagnosing skills or decision making, and this could be done via text-to-text or via voice-to-voice interaction. The most advanced thing you can create with GPT-4 is the custom GPTs, which can serve to create very complex scenario simulations. And for this presentation, I created 3 GPTs for various professions, helping professions context, and here is an example of a therapy practice trainer which simulates realistic client interactions, and I will talk about it more in a detail later. For a demonstration how a simple prompt to generate a case or a scenario could look. You have an example here. However, the prompts like this could be very simply adapted to any context or your particular learning situation you have. And from a prompt like this, when you assign the chatbot a role of a medical expert in medical education and so on, you can generate a case where there is a detailed patient profile, a clinical scenario, which is the students going to face, but more importantly, you get clearly defined educational objective and the questions for the students. They can then work on this like their homework or depends on your context. What is important to consider here is that you as an educator, it's always necessary to critically evaluate the output of the chatbots, because the models could hallucinate and you are responsible for the factual correctness of the learning materials you will be providing for the student. So please don't underestimate it. It is really important for you to really check the materials before you are going to use it. And this is already an example of custom instructions. In this case, the instructions are becoming a part of the system prompt of the chatbots, and the advantage here is that they are not visible to the student. And the interaction in this case could be voice to voice, or text to text, so you can just prompt the chatbot, and the students do not know what for simulation or patient or client scenario is behind the simulation. So it's quite realistic. And I'm going to play you example of the voice-to-voice interaction now.
Hello, what brings you to the doctor?
Hi, I've been having these weird episodes where I feel tingling and numbness in my hands and feet. It's been happening on and off for a while now, and sometimes it's accompanied by this intense fatigue that just knocks me out. I'm also experiencing some migraines and blurred vision. It's all starting to affect my work and daily life, and I'm really starting to get worried about what's going on with me.
When did you start to notice?
It's hard to pin down exactly, but I think these symptoms started cropping up a few years ago. They've become more frequent and noticeable over the past year. The numbness and tingling come and go, sometimes lasting a few days before disappearing again. The migraines and blurred vision have been more recent, maybe over the last few months.
Okay, so you see this is quite realistic. What is great is that there is a transcript of the conversation running behind, so you will get a perfect transcript of the interaction for the students to review the interaction, or for you, you can ask the students to hand the transcript for you to evaluate the interaction. What is also great that the simulation is running very naturally, in the way that in the moment the student gets stuck, he can or she can simply ask, okay, I'm not sure what to do next, could you please provide me with some hints, or could simply ask for a feedback on the whole interaction, and it's really happening in a very natural way. So another way you can use the chatbots is creating custom GPTs, and in this case, you as a creator of these, you are providing it with a knowledge base. So this means that you can basically provide some example scenarios you want the chatbot to choose, or you can provide your own learning materials or some scientific texts which should enhance the accuracy of the simulation. In the GPT-4 there is an inbuilt GPT builder, so it's quite easy and simple for anyone to construct a learning aid like this. And yeah, again, I will run an example for you, and all these GPTs will be freely shareable very soon. So at the end of my presentation, there is a QR code where you can download the whole presentation with the links, and you can try to interact with all the examples I will provide you today by yourself, and to evaluate if you find it useful or not. Okay, so the demonstration.
Start new patient simulation.
Great. Let's begin a new simulation. Today, you're responding to a call regarding a middle-aged male who has collapsed at a local park. When you arrive, you find him lying on the ground, conscious but appearing dazed and confused. He's breathing rapidly and clutching his chest. As you approach, he looks at you and says, I feel like there's a weight on my chest, and I can hardly breathe. What will you do first?
I will check his heart rate.
A good choice to check his heart rate, as it gives immediate insight into his cardiac function, especially given his symptoms of chest pain and difficulty breathing. As you check, you find that his pulse is fast and irregular. This could indicate a potential cardiac issue that needs urgent attention. What's your next step?
I would ask if he hit his head when he fell down.
Yeah, okay, so from this you can clearly see that I am not a medical specialist. I was quite lost during this training. And again, you are getting transcript of the whole interaction for you to review. And also you can see the variations of this GPT as a simulators for social work training or for therapy practicing and so on. So it's up to you to try it if you are interested. You can also create customized chatbots in applications like Character AI, where the user creates customized AI characters providing descriptions and example conversations, and these characters are then able to have realistic conversations. They understand context, can remember the previous interactions, and they are also trained by the user feedback, where you evaluate the quality of the response. And again, for this presentation, I created 3 characters. A bridge psychologist, a physician who is here to provide guidance to medical students, but also an expert mentor for social work students. And again, what I need to mention is with these custom characters, you have to communicate as a user by typing the text. However, their response could be in voice. So this is what you are going to see in this demonstration. So let's start with the psychologist.
Sure. I'd be happy to give you a case scenario so you can practice proposing the appropriate intervention. A young adult comes to you seeking help for feelings of anxiety and low self-esteem that have been affecting them for several months now, and have been making it hard for them to get through their daily routine. They have been experiencing intrusive thoughts and a sense of dread about the future, and they are finding it difficult to focus on their work and relationships. What would be your approach to helping this person? There are several different approaches that can be taken with a case such as this one, depending on the needs of the individual and the specificities of the situation. Some possible options include: 1. Cognitive behavioral therapy is an evidence-based approach to treating various psychological issues such as anxiety.
Okay, and a quick look into the social work.
Sure. Here's a scenario for you to try. You're working with a single mother who has experienced domestic violence and is currently unemployed. She shares with you that she's feeling anxious and overwhelmed by her situation and doesn't know where to turn for support. In this case, what could be the right intervention for you to propose? That sounds like a good first step. Community centers often provide services and resources for people in need, and they can be a...
Okay, so after the lunch, there is a workshop where we will be testing these agents and all of these examples in real life, so you can tell me if they are really addressing the issues correctly, and I'm really curious about it. You can also use more complex workflows to create animations like this. These are not interactive, however, I think that they could be a nice starting point when teaching about diagnosing or assessing patients. So let's have a look.
Dobrý den, pane doktore. Posledních pár týdnů mám velké potíže. Teče mi z očí i z nosu a svědí mě. Často kýchám. Je to opravdu nepříjemné.
I just can't shake this feeling of constant worry. I worry about everything, work, health, even small things seem overwhelming. I've been feeling so restless lately. Nights are the worst. I just lie there with these thoughts racing, and I can hardly sleep. It's exhausting.
And I think after a presentation like this, the students could discuss about what would be the next step to best assess the situation. And to create animations like this, I usually use ChatGPT-4 as a reasoning engine to tell me or to provide me the description of the prompt for the text-to-image model to have the image of the person with the diagnosis visible. Then I ask it to provide me with the text, what would a patient like this tell the doctor, what would be the typical sentences, and then I feed this to the text-to-image model, Midjourney or DALL-E, and then the image and the script is fed into DID platform, which uses text-to-speech model and then connects it with lip synchronization, and this is the result you can get. And I'm coming to the most advanced examples. These are multimodal agents. This is a beta version from DID platform, and to create an agent like this, you provide an image, you provide the description of the behavior, you provide knowledge base from which the agent draws information during the interaction with the user. And what's best, the interaction is real time and it's voice to voice. So I think this is one of the most realistic learning simulations you can provide to your students. And I'm going to show you the demonstration.
Tell me something about your life history.
Okay, he's thinking, the agent is reading the knowledge base.
I grew up in a Midwest city with my mom and 2 siblings. My parents split when I was young, and I had a rough time in school due to the unstable home life. I dropped out at 16 and worked odd jobs, but things got tough after a workplace accident.
Where is your family and for how long have you been living on the street?
I've had sporadic contact with my kids who live with their mom. I regret not being there for them. I've been living on the streets full time since my car got taken away. Tough times, you know.
Okay, and the other agent I created is Emma, who is heroin addict.
Hello, could you tell us something about your life history?
Hey, I'm Emma, heroin addict. I was born in a suburban area on the East Coast. I'm an only child. My parents divorced when I was 12, and I with my mum, who had mental health issues. My dad was pretty absent, and I struggled in my teenage years.
Okay, I'm going to stop her, but animations like this could help the students to practice their interviewing or interaction skills with the patients or clients. And we are coming to the last example of the experimental tools, which are quite new now. Here I'm presenting you an empathetic AI, which is called Hume. And this AI, you can use it via voice-to-voice interaction, where it labels the emotions during the conversation, or you can use webcam and let it label your facial expressions. So this is my last demonstration.
Hello, could you greet the audience at a conference?
Hey there! Absolutely, I'd love to greet the audience at a conference. How can I help set the stage for this exciting event?
Just explain how you can read emotions from voice.
Oh, great question. I can read emotions from voice by analyzing tone, pitch, and other vocal cues. It's all about capturing the subtle nuances in how you speak to understand your feelings. Cool, right?
How could you be used for education of helping professions?
Yeah, let's clear that up. Absolutely. Our empathic voice interface can be a valuable tool in education for helping professions. It can assist in training and simulations, providing support and feedback to aspiring professionals. It's a powerful way to enhance learning experiences.
So this was the last demonstration, but you can imagine that all these examples I presented to you, all these techniques are coming to merge together. So we will have multimodal agents which will be responsible to emotions, and we are just on the beginning on the way how to integrate best these tools into education where empathy training is necessary, especially for the helping professions. So this was all from my presentation. You are welcome to download it in the PDF. All the links are available for you to experiment with. If you are interested into how these examples were created and what are their limitations and want to play with it and experiment, you are welcome to join my workshop after the lunch, and good luck with AI and experimenting, and I hope the educators were inspired at least a little bit. Thank you.
Questions?
I would be interested, so for the specific types of agents that you have shown which actually interact with the students and even give them advice, so basically the material cannot be pre-screened. What is the, I mean, under what context do you believe they are appropriate, and what is the danger of them actually giving wrong instructions and teaching wrong things to the students? So this is something that, yeah.
Well, during construction, and you can choose the agent to only use the knowledge base and not its training data. You can make it hybrid, that it will have some option to draw the information or generate its own based on training data, or you can just let it free, just without any knowledge. So for cases where you want to be sure that it's providing factually correct information, I would prepare a very complex and detailed knowledge base and restrict the agent to only work with the information provided within the knowledge base. However, nothing is perfect, especially with generative AI, and that is something what I'm interested also in. What are actually the limitations and how responsible the use of learning aids like this is, because it's quite fresh, and yeah, we have to experiment to find out.
Another question? There is no other question than the last question.
Lovely, thank you. Have you thought about making this part of the, so there's a micro-credentialing effort going on at Charles University, and something like this could become a really interesting framework for a lot of these short courses. Is that part of what you're thinking about? So meaning to actually provide course material, and then what would the certification look like for students?
Well, this was my first attempt in this area, so this just was developed based on my brainstorming 2 weeks ago. And I was curious about the feedback, and if someone actually finds it useful, I think it will be great to cooperate and to it would be great to have a course if someone really finds this useful, and I hope that someone will, because we need to implement the AI into the education, and this could be a very nice step.
Thank you again. This is the last time we are meeting all together, because in the afternoon there will be workshops and we'll be separated in at least 2 different rooms. So let me take the opportunity to thank the people and institutions that got involved in organizing this. So let's thank Campus Hybrnská for hosting us here. Charles University and the Faculty of Mathematics and Physics for financial support. And the team, Josef Šlerka and Aleš Bartoš, who are experiencing some health problems and couldn't come today, but were part of the program committee, and the people who are here, Lukáš Kačena from prg.ai, who will be organizing the workshops in the afternoon, Martin Vita, and David Hoxa, who are here among us. Thank you, guys. We'll be having some refreshments, and the workshop starts at 1:30. And does anybody of you want to say some instructions about the workshops? Martin? Not now? Okay, so lunch and then 1:30 workshops. And thank you all for coming.